What are the implications of dark energy for the ultimate fate of the universe? Picture the universe as a silent ocean that expands slowly, like a tide that advances unhurriedly. Galaxies are islands of light in this dark sea, and with each passing second, the space between them stretches just a little bit more. We've long known that the cosmos was expanding. What took us time to realize is that this expansion isn't just continuous, it's accelerating. Something is pushing the fabric of space outward, a gentle, persistent, invisible shove. We call this dark energy. It's not wind, it's not matter, it's not hidden stars. It's a property of space itself, as if the elastic band holding everything together were for some reason giving way at an increasingly rapid pace. How do we know this without leaving our cosmic neighborhood? We observe natural beacons, explosions of distant stars that shine with predictable intensity. When we compare the brightness we expect with the brightness that actually reaches us, we can tell how much space has stretched along the way. The light arrives stretched, shifted toward redder tones, and this measurement reveals the history of expansion. That's how we detected the acceleration. Distances are growing faster than they would if gravity alone controlled the game. Put simply, it's not enough for gravity to pull, there's something pushing. This thing doesn't behave like anything we know in everyday life. Matter, like us, planets, dust, gas, pulls. Dark energy pushes, and it does so without preferring any direction, without forming clumps, without emitting light. By our best current measurements, if you divided the universe into 10 portions, roughly 7 would be dark energy. The remaining portions would be split between matter invisible to the eye, dark matter, which pulls but doesn't shine, and ordinary matter, the minority that builds stars, planets, and people. It's a counterintuitive picture. What decides the rhythm of everything is precisely the component we don't see, only infer from its effects. When we think about the universe's ultimate fate, the central point is this: what dark energy does to the future depends on how it behaves over time. If this push remains constant, expansion will continue accelerating in a controlled manner. If it grows stronger, the acceleration could become so intense that it undoes structures. If, on the contrary, it changes nature and weakens, gravity might regain some control. The implications aren't philosophical, they're mechanical. It's the tempo of the tide that changes the shape of the coastline. Over the next few billion years, the clearest consequence is the reorganization of the distant sky. Nearby galaxies, bound by gravity, will continue together, dancing with each other until they merge. But those beyond our cosmic neighborhood will drift farther and farther away. The observable universe of a distant future will seem emptier, not because things have disappeared, but because their light will no longer be able to reach us. It's not a wall, it's not a vanishing act, it's a limit of influence, like waves that no longer reach the shore because of distance and the rhythm of the tide. If dark energy is indeed nearly constant, a push that neither grows nor diminishes, the most likely fate is a slow, prolonged cooling, what textbooks call the Big Freeze. In this scenario, accelerated expansion doesn't tear apart atoms or break up solar systems by itself. It merely separates the large clusters that weren't firmly bound together. Within gravitationally bound groups, galaxy mergers continue to happen. Stars keep being born as long as there's gas, and that can last a very long time. But raw materials aren't infinite. In a very distant future, the manufacture of new stars will become scarce, and the sky, as seen from any planet that still exists, will be more sparing with its fireworks. This long future can be measured in simple terms, trillions of years. Small stars, the most economical ones, burn fuel extremely slowly and can shine for periods unimaginable to us. As long as they exist, there will be light, heat, and chemistry. Then they too run out. White dwarfs, hot shells of what were once stars, cool slowly like embers losing their red glow. Brown dwarfs, stars that never fully ignited, remain warm dark. It's a calm inventory of what remains, not a tragedy. The cosmos doesn't go out with a snap, it turns down the volume degree by degree. Far beyond these trillions of years, the universe enters an era dominated by remnants, rogue planets, dead stars, and black holes. Black holes are persistent but not eternal. Physics predicts that on almost unpronounceable timescales, they too lose energy, very slowly, until they evaporate. It's the kind of process that strains the imagination, time so long that the word trillion seems like the beginning, not the end, of counting. If dark energy is constant, it doesn't interfere with these local clocks. It merely maintains, in the background, a stage that's increasingly vast and cold. There is, however, another possibility. If dark energy's push grows over time, if space itself becomes increasingly eager to expand, a scenario emerges called, with some drama, the Big Rip. Think of this as a tide that not only rises, but gains strength with each wave. First, galaxy clusters fall apart. Then galaxies themselves stop holding together. Next, solar systems would lose their stable orbits. In an extreme phase, matter itself would be affected, and in the final moments, even atoms would have their bonds torn apart. This isn't an announcement, it's a hypothesis. Current measurements don't require this path, but they don't rule it out with absolute certainty either. What decides is how fast the push grows. There's still a third type of ending, rarer in conversations because today it seems less compatible with the data. What if dark energy isn't permanent? What if it's a temporary state that can change sign or lose strength? In that case, expansion could decelerate, stagnate, and even reverse, leading to a big crunch, a general retreat. There are variants that try to combine retreats and expansions in cycles, like very long breathing. We don't need to adopt any definitive picture here. It's enough to recognize that the important question is always the same. How does this push behave over time? To understand why this matters so much, return to the image of a balloon with dots drawn on it. It's not the air inside the balloon that flies somewhere, it's the rubber that stretches. If the rubber stretches at a constant rate, the distance between dots doubles at regular intervals. If the rubber starts stretching faster, the dots separate in an accelerated manner. Nothing needs to pull from outside. The material itself decides the dance. The universe's ultimate fate is essentially the long story of how this rubber behaves over time. There are curious implications for anyone who, in a distant future, tries to reconstruct cosmic history. As accelerated expansion pushes distant galaxies beyond our observable horizon, some of the clues we use today become unreachable. The background light left by the universe's hot beginning, a cold glow that fills everything, becomes so stretched that it blends into noise and disappears from practical access. On unimaginable scales, an isolated observer could look around and see only their island of merged stars, without clear evidence of a vast universe out there. Context fades with distance. For life, dark energy doesn't impose a sudden end. In a slowly cooling universe, what we'll have are windows of opportunity of very different durations. Massive stars live briefly, small stars live long. Around some of them, worlds can exist for times that, compared to the universe's current age, seem like eternities. Even when stars cease, there may be residual heat, slow chemistry, alternative sources of local energy. None of this guarantees permanence. It merely shows that the cosmic calendar isn't made of extremely short deadlines. It's a vast calendar with pages we turn slowly. In our neighborhood, for example, there's a long-term prediction that's independent of dark energy. Our galaxy and Andromeda should merge in just a few billion years. This merger isn't a collision of stars, but a dance of gravity, with orbits reorganizing and gas clouds compressing here and there. Dark energy doesn't prevent this. It acts on larger scales, in the space between neighborhoods, not in the building's hallway. After this merger, the resulting family of stars will become increasingly isolated from the rest of the visible universe. From the perspective of those measuring the cosmos today, dark energy imposes a type of meticulous work. It's not enough to know it exists. We need to know if it changes. For this, we compare light clocks at different distances, study how matter distributes on large scales, observe how space's geometry itself curves the light paths from background galaxies. It's a patient effort, like listening to a distant metronome and trying to perceive whether it's gradually accelerating or not. 1,000 small observations compose an answer that doesn't fit into a single night. There's also a troubling question. Why does the intensity of this push have the value it has? If it comes from vacuum energy, from quantum activity that never quiets, even in nothingness, then theoretical calculations tend to greatly exaggerate the result. The universe wouldn't be here, so calm and long-lived, if the push were as strong as some crude predictions suggest. This tells us, calmly, that a piece is still missing from this puzzle. We still need to discover the exact mechanism, the precise form, perhaps a new connection between ideas we still treat separately today. When we look at the ultimate fate, it's good to remember what doesn't change. Gravity continues to be the thread that sews nearby things together. Heavy stars will continue being born and dying, producing elements as long as there's gas for it. On a larger scale, dark energy keeps stretching the stage, and the horizon of what we can see and touch keeps moving away. The fate, then, isn't a single event. It's a transition of rhythms, from a noisy universe full of star formation to a quieter universe of slow processes. If we someday discover that the push grows, we'll know there's a deadline for each level of structure. First the largest break apart, then the medium ones, and finally the smallest ones. If we discover that the push is constant, we'll know that local structures have a gigantic survival time, and that the end is, in practice, a cooling without defined final terms. If, surprisingly, the push retreats, we'll rewrite the last chapter, with gravity regaining the floor. In all cases, the common thread is the same: measure, compare, test. Meanwhile, here and now, what we do is observe and fine-tune instruments. Each distant supernova we measure is one more step in the map of time. Each galaxy map, each gravitational lens, each subtle trace in the universe's background light adds a mark to the notebook. The ultimate fate doesn't depend on us, but understanding it does. And understanding, for science, is simplifying carefully until ideas that span scales of trillions of years fit into a calm sentence. Perhaps the best image to take with you is again that of the tide. Dark energy is the tide that rises so lowly that we only notice when we compare photographs taken decades apart. On the surface, the beach remains the same. Waves break, stones stay in place, but the general level changes. Today, we can measure this change, and it tells a story of gradual distancing, of skies that, over the ages, become more equanimous with distant galaxies, more generous with silence. Ultimately, the implications of dark energy for the universe's ultimate fate are a catalog of compositions: what stays together, what separates, at what pace cold sets in. Nothing here requires haste or fear. It requires attention. The universe has already given us enough clues to know that expansion is accelerating. What remains is to know with the same clarity whether this acceleration is a stable habit or a phase. That's what differentiates an ending in slow cooling from an ending in rupture. Until then, we continue describing this push with the best care we can. We continue comparing light clocks and galaxy maps refining our listening for a metronome that beats in the depths of the cosmos. And while this listening sharpens, we can rest in this serene observation. The fate, whether it's a cold silence or a more dramatic tearing apart, isn't an abrupt fall, but a transition dictated by a rhythm we're learning to read. The universe, with its invisible tide, continues, and we continue looking slowly, with patience, sentence after sentence, measurement after measurement. Rogue planets that don't orbit any star exist and are detected by infrared emission. Rogue planets are worlds that travel alone, without orbiting a star. They have planetary mass, generally somewhere between Jupiter's mass and several times Jupiter's mass, though there are signs of smaller objects too, and follow their path through interstellar space. The natural question is, how do we find something that doesn't receive light from a nearby star? The answer has two parts. Young worlds are still hot from the heat of their own formation and therefore glow in infrared. Older worlds cool down and become invisible. In those cases, the clue comes from a gravitational effect that temporarily increases the brightness of a background star when the planet passes in front. These two techniques, infrared and microlensing, support almost everything we know today about starless planets. Starting with infrared, a newborn planet retains heat for millions of years. It's not visible light like from a light bulb, it's thermal glow like from a warm stovetop. Sensitive cameras installed on telescopes in Chile, Hawaii, and in space can record this heat. The procedure is relatively straightforward. Surveys sweep regions where many stars are born, compare colors. In infrared, very young objects appear red, and then use spectra to look for signs of youth, like traces of low gravity in the atmosphere. When the candidate also moves along with the group of young stars in the region, the suspicion is confirmed. It's a solitary body with planetary mass without a companion star. This approach has revealed dozens of objects in young stellar associations relatively close to us. In some of these places, the map shows an entire population of isolated worlds all at once. The known age of the region helps estimate mass and expected brightness, and comparison with models indicates that many are indeed in the planetary range. The key point: they appear because they're still hot. As time passes, they cool down and disappear from the reach of these cameras. Infrared also allows us to peek at physical characteristics. Even without a nearby star, it's possible to study atmospheres, see traces of water vapor, methane, mineral clouds, and fine dust. Notice if brightness varies for hours, indicating rotation and weather with cloud patches coming and going. In several cases, light changes intensity periodically, suggesting days that last just a few hours, like Jupiter. It's a clean laboratory, without the glare of a star, for understanding how clouds, winds, and chemistry work in gaseous worlds. In recent years, another piece has emerged: pairs of Jovian mass objects wandering together without stars, identified in stellar nurseries observed in infrared by modern space telescopes. These doubles show that not every rogue planet was kicked out of a system. Some may be born already free when the gas cloud fragments into very small pieces. It's a clue that there are at least two pathways of origin. When the planet is old and cold, infrared isn't enough. That's where gravitational microlensing comes in. The idea is simple: chance alignments. If a massive object passes in front of a more distant star, gravity acts like a magnifying glass and increases the star's brightness for hours or days. If the magnifying glass has planetary mass and there's no star attached to it, the event is very brief and shows no signs of a host. Surveys that monitor millions of stars in the sky record these brightness spikes, and with the shape of the light curve, can infer the approximate mass of the body that passed. This has already revealed candidates not only with Jupiter's mass, but also with smaller masses, in events that lasted less than a soccer game. The two windows, infrared for young ones, microlensing for cold ones, complement each other. With infrared, we characterize individuals, temperature, clouds, rotation. With microlensing, we map the cold population, which is probably the majority, because every isolated planet eventually cools down. Together, they give a more honest portrait. Rogues exist at different ages and sizes. How do these worlds end up without stars? Two pathways explain well what we see. The first is planetary. In young systems with several gas giants, chaotic gravitational interactions can eject one of them right at the beginning of the system's life. It's the natural pushing and shoving of many heavy bodies trying to share the same space. The other is miniature stellar. Sometimes the gas cloud that forms stars fragments into very small pieces, which collapse without ever getting to ignite as stars. These pieces can have planetary mass from birth. The free doubles favor this second pathway in some cases. In other regions, the number of rogues matches better with the idea of ejection. Both probably contribute. How many exist? There's no final number, but clues point to many. In certain nearby young regions, we count dozens to more than 100 solitary worlds with planetary mass. On galactic scales, microlensing surveys suggest that Jovian mass rogues aren't rare. There are signs of even smaller objects too. Uncertainty remains because it's hard to transform a local sample into a galactic total, and because separating actually free from planet very far from a faint star requires following the target for years. The working consensus is they exist in relevant numbers and are part of the normal story of how systems form and evolve. What would one of these planets be like up close? In a young one, the sky would be dark with no sunrise, but the planet itself would emit heat. Its atmosphere could have thick clouds, strong winds and storms, like the gas giants we know. Without starlight, temperature and climate depend on internal heat, which decreases over millions to billions of years. Moons. It's possible some have moons, especially if they were born by fragmentation, but detecting moons on rogues is beyond what we can do today. Magnetic fields and auroras are also plausible in gas giants, but again, measuring this directly on an isolated object is a challenge. Do they represent any risk to us? The chance of a solitary planet passing near the solar system in human timescales is tiny. On scales of millions of years, massive objects that cross very close by could disturb comet clouds at the edges of our system. But that's textbook scenario, not a practical concern. For us, the impact is scientific. Understanding these bodies improves planet formation theory and the dynamical evolution of systems. A point that often confuses is the boundary between planet and brown dwarf, which are slightly more massive objects, almost stars that don't manage to shine like the sun. In practice, the distinction requires knowing mass and age with some precision. In young regions, we can link the object to a group of clock stars, and from there, better estimate its mass. Outside of that, classification can get gray. Still, the general picture doesn't change. We find many starless bodies with masses in the planetary range, and they behave like cold, dark, gaseous worlds. On the instrument side, the strategy has become increasingly clear. For infrared, sweep large areas in stellar birth regions, filter by very red colors, confirm with spectra, and then measure proper motion and distance over years. This separates the group member from the background intruder. For microlensing, high cadence monitoring in dense stellar fields global coverage to not miss peaks that last just a few hours, and, when possible, follow-up observations with adaptive optics to check if there's a faint star nearby. It's ant-like work, but one that has already made big leaps in just 1 decade. And what's coming? 3 fronts should change the scale of the problem. The first is a space telescope dedicated to microlensing, which will observe from space for long periods and should record thousands of events with stability and precision difficult to achieve on the ground. The second is a new wide-field observatory in Chile, which will photograph the southern hemisphere sky for 10 years, allowing fine measurements of proper motion and variability. Great for finding young rogues and, as a bonus, supporting microlensing. The third is the continuation of the space telescope that observes in infrared with high sensitivity, capable of better separating clouds, molecules, and temperatures in very young objects. These 3 pillars, more cold statistics, more young candidates, more atmospheric characterization, should transform findings into measured population. Why does this matter beyond curiosity? Because the amount of mass the galaxy puts into very low-mass objects influences the chemistry of the interstellar medium, the frequency of environments where planets can form, and the very dynamics of star clusters. If ejection is very common, maybe many planetary systems go through chaotic phases right at the start. If miniature fragmentation is efficient, we need to adjust the theory that describes how clouds break apart when forming stars. In both cases, data about rogues function as an independent test. They force theory to match reality. Some observational details help calibrate expectations. In images, very young starless objects appear exaggeratedly red in infrared filters, precisely because their clouds and dust hold back light at certain wavelengths. In spectra, lines of light elements appear weaker than in older objects, a sign of low surface gravity, that is, they're still fluffy, not yet compressed. In photometry over hours, it's common to see light vary a bit and repeat a pattern as if a band of clouds were rotating in and out of our field of view. Putting it all together, you can tell a physical story, not just point and say, "There's one there." In microlensing, the secret is the light curve. It rises, reaches peak, and falls symmetrically. The duration and shape of the peak tell us the lens object's mass. Very short events without a host star signature are the best candidates for free planets. The limitation is that the event doesn't repeat. Either you were looking at the right time or you missed it. That's why surveys work as teams, with telescopes at different longitudes to cover the entire night. In the midst of all this, there's caution. Parts of the topic are still active and change with new data. Estimating how many rogues exist in the entire galaxy is still an exercise with wide error bars. Definitively separating free planet from distant companion of a dark star is difficult and requires years of follow-up. And transforming spectra into mass and radius depends on atmospheric models that are still being adjusted for very low gravities. But the direction is clear. Samples are growing, methods are sharpening, theoretical scenarios are becoming more constrained. Summarizing the essentials, planets that don't orbit stars exist. Young ones are seen because they're still hot and glow in infrared. Old ones appear as gravitational magnifying glasses that brighten stars for a few hours. They can be born free when clouds fragment into small pieces or become free after gravitational fights in young systems. We've already found dozens to hundreds in formation regions. There are signs of many others scattered through the galaxy at various masses. Studying them helps understand how planetary systems begin, how they evolve, and how much miniature matter our galaxy manufactures. Galaxies rotate, and they rotate fast. So fast that if we only counted the matter that shines, stars, illuminated gas, heated dust, many of them should fall apart like water in a spinning, uncovered bucket. But they don't fall apart. They remain cohesive for billions of years. That's the starting point. There's more gravity than visible light can explain. How did we reach this conclusion? By measuring velocity. Light from stars and gas carries a velocity stamp due to the Doppler effect. When something approaches, the spectrum shifts slightly toward blue. When it moves away, toward red. In galactic disks, one side approaches us and the other moves away. With spectrographs, we trace a velocity map along the galaxy's radius, from inner regions to outer ones. We do this with bright gas lines near stars, and farther out with the radio signal from neutral hydrogen, the famous 21-centimeter line, which reveals the movement of cold gas far beyond the luminous edge. What would classical gravity suggest if mass were concentrated where light is? Near the center, velocities might increase, but beyond a certain radius, as you move outward, the effective gravitational force should drop, and orbital velocity should too. In direct terms, after a peak, the curve should decline. What we observe, however, is the opposite. The curve tends to stay flat. Stars and gas continue rotating fast, at 150 to 250 kilometers per second in many spirals, even where there's little light. This isn't the technical detail. It's a pattern repeated in large, medium, and even dwarf galaxies. Something keeps gravity strong in the outer regions. The history of this discovery has important names. In the 1930s, Fritz Zwicky had already noticed in galaxy clusters a mass deficit. Galaxies within clusters were moving too fast for the visible gravity, adding up light from all of them. Decades later, in the 1970s, Vera Rubin and Kent Ford measured rotation curves of spiral galaxies with great precision and showed that the flattening of velocities was the rule, not the exception. Gradually, it became hard to escape the conclusion: vast amounts of invisible mass surround galaxies. We call this component dark matter. Dark not because it's black like ink, but because it doesn't shine, doesn't absorb, doesn't reflect light in measurable ways. The best image is that of a halo, an extensive cloud of mass that surrounds the disk of stars and extends far beyond it. This halo provides the extra gravity needed to maintain fast orbits without the galaxy falling apart. In broad numbers, most of the mass in a typical galaxy isn't in the bright disk, it's in this invisible halo. Is this just a useful hypothesis? No. The idea of dark matter is supported by independent lines of evidence. 1. Gravitational lensing. Gravity bends light. In massive clusters, we see arcs and multiple images of background galaxies, signs that there's much more mass curving space than visible light indicates. Even when the effect is weak, we can statistically feel mass distribution by mapping small distortions in the shape of many background galaxies. These mass maps match the need for dark halos. 2. Hot gas in clusters. X-rays reveal that clusters are filled with gas at tens of millions of degrees. For this gas not to escape, you need a deep gravitational well, much deeper than the massive visible galaxies would explain alone. Again, the math works out with dark matter. 3. The bullet cluster. In a collision between two clusters, visible gas experiences friction and lags behind, but the mass inferred by gravitational lensing moves forward with the galaxies. This separation between where the gaslight is and where the mass is a direct portrait of a component that barely interacts, doesn't collide, only pulls gravitationally, exactly what we expect from dark matter. 4. Cosmic microwave background and large-scale structure. The small temperature ripples left by the universe's infancy, measured by satellites, have a pattern that depends on how much ordinary matter and dark matter there is. The best fit calls for much more dark matter than normal matter. Later, as the universe grows, we simulate how these ripples grow and become the cosmic web of galaxies. Observed maps match well with simulations that include cold dark matter halos surrounding everything. If the main explanation is there's mass we don't see, what would this mass be? It's not ordinary cold gas, because gas would absorb or emit in radio and infrared. It's not dust, for the same reason. And it can't just be burned out stars, planets and rocks in sufficient quantity, because this runs into brightness limits and into how light elements like helium were created in the early universe. The picture that best fits is of new particles, different from those that make up atoms, that feel gravity, barely feel light, and interact very little with ordinary matter. Cold here means they were moving slowly in the early universe, helping to form small structures first, which then joined into large ones, as we see. An honest aside, there are alternative proposals that try to explain rotation curves by changing the law of gravity at very small accelerations instead of adding matter. The best known of these ideas, MOND, gets many details of individual curves right, especially in dwarf and low luminosity spiral galaxies, using a very low acceleration parameter as the problem's constant. But these theories, in their various versions, face difficulties when we look at the full set of evidence: clusters, lenses, microwave background, and cosmic web evolution. To date, the combination standard gravity plus dark matter is what explains the most different things with the same set of ingredients. Back to galaxies, what's the general distribution of this halo? In simulations, density falls smoothly with radius, without a hard edge, and concentrates more mass in inner regions than outer ones, but in a way that keeps gravity relevant well beyond the light. Standard profiles emerge naturally when we let cold dark matter collapse over billions of years. In the most central regions, especially in small galaxies, there are active discussions. Observations sometimes suggest more uniform cores than original simulations predicted. Processes involving gas, supernova explosions pushing matter out and in, for example, can soften the halo's center. Modern simulations that include these feedback recipes better reproduce the data. And our galaxy. The Milky Way disk rotates at something like 220–230 kilometers per second in the Sun's neighborhood. With only the mass of stars and gas, this velocity would drop at the edges. To maintain the pace, we infer a dark matter halo that extends well beyond the disk and central bulge. Estimates place the Milky Way's total mass at about 1 trillion solar masses, with most of it in the dark halo. Locally, in our neighborhood, the dark matter bath is very tenuous, extremely sparse, but sufficient for Earth-based experiments to try capturing it passing through detectors. Speaking of which, that's another front: how to detect the particle, not just the gravitational effect. 3 main strategies exist. The direct approach, in underground laboratories, tries to observe the extremely rare collision of a dark matter particle with an atomic nucleus in a shielded detector. The indirect approach looks for byproducts, like gamma rays, from annihilations or decays in regions with lots of accumulated dark matter, like the galaxy's center or dark dwarf galaxies. And the collider approach tries to produce the particle in accelerators, like the LHC, inferring its presence from missing energy in collisions. So far, nothing conclusive. This doesn't disprove the hypothesis. It pushes the search toward more subtle masses and interactions. And it opens space for other candidates, like axions, which require different experiments: microresonators, magnetic fields, extremely sensitive microwave cavities. There's also neighborhood science that tests dark matter without looking directly at the particle. Here are some useful examples. Dwarf satellite galaxies. The quantity, orbits, and velocities of these small galaxies around the Milky Way and Andromeda serve as a laboratory for the dark matter model. Classic problems like too many satellites and the big ones that fail, predictions of denser halos than we observe, have been mitigated as simulations better included the role of gas and observations became more complete. There are still points of tension, but the picture is more consistent than 10 years ago. Wide-area weak lensing maps. Recent surveys statistically measure how total mass, visible plus dark, slightly deforms the shape of millions of background galaxies. Comparison with what's expected from structure growth in a universe with dark matter and dark energy tests the model on large scales. Results are generally compatible, with small differences that motivate improvements in data and theories. Gas and stars in low surface brightness disks. These galaxies have little stellar weight per area. The halo dominates gravity at almost every radius. Their rotation curves are a clean test of the halo. In many, the flat curve persists as far as gas can be measured, tens of thousands of light years from the center. All this converges on the simple statement from the beginning: galaxies rotate too fast to hold together with visible matter alone. The gravity surplus requires additional mass distributed widely. The dark matter interpretation isn't the only one considered, but it's the one that best ties together rotations, lenses, clusters, microwave background, and cosmic web all at once. What changes if we fully accept this picture? In practical terms, we start seeing galaxies as islands of light, immersed in much larger dominant halos. Galaxy formation becomes a story of how gas falls into these halos, cools, forms stars, lights up, and sometimes goes dark. Disk evolution, their bars, spiral arms, starbursts, happens within the halo's gravity well. Interactions and mergers between galaxies stop being just disk encounters. They're halo encounters with tidal effects and drag that shape the cosmological landscape. And what's ahead? New maps and more precise counts. Telescopes dedicated to measuring weak lensing over large areas of the sky will refine mass distribution at various scales. Observatories that repeatedly image the sky over years, monitoring brightness and position, will more accurately measure the mass of individual galaxy halos and clusters. In radio, new networks sensitive to neutral hydrogen at great distances will extend rotation curves and trace gas even farther from the disk. In particle searches, larger, quieter detectors with new technologies continue digging into the noise floor, and in parallel, alternative theories continue being tested where they're strongest, because that's how science advances, looking for where the favored explanation might fail. In the end, the statement that galaxies rotate too fast to hold together with visible matter alone is a faithful synthesis of half a century of measurements and half a century of confirmations by independent methods. It doesn't require formulas to be understood. Just accept that measured velocity far from the center is too high for the light we see. The solution that best fits everything else is that there's more mass out there, discrete, transparent, and ubiquitous, shaping orbits and keeping star islands cohesively intact for billions of years. It's this component, silent and dominant, that we call dark matter. Comet Shoemaker-Levy 9 collided with Jupiter in 1994, recorded in detail by Hubble. July 1994. For 1 week, the solar system had a scheduled appointment for a spectacle no one had ever seen before, a comet arriving at Jupiter in single file, piece by piece, and diving into the planet as if each fragment were a chapter. It was the first collision between solar system bodies observed in real time, and it happened at the perfect moment. The Hubble Space Telescope had just received new eyes in the 1993 repair mission and was ready to show details that, until then, had been impossible. The story begins the previous year when 3 comet hunters, Carolyn and Eugene Shoemaker and David Levy, noticed something strange in the images. Instead of a single, blurred spot, a string of beads like pearls on a thread. The explanation was both elegant and violent. On its previous passage, the comet's nucleus had come too close to Jupiter, crossed the safety limit, and been torn apart by the giant's tidal forces. What remained was a train of fragments in the same orbit, separated by small velocity differences. The convoy was named Shoemaker-Levy 9. The pieces received letters for identification, and calculations said something straightforward. In mid-July 1994, that lineup would cross Jupiter. For the first time, astronomers had a dress rehearsal, a set stage, and a premiere time for a collision. When the day arrived, expectations were clear: hypersonic entries, energy release at altitude, plumes rising, marks appearing. But seeing it happen, step by step, is different from imagining it. The first visible impact confirmed the script. From the planet's illuminated side, there was no cinematic explosion at the moment of entry. The initial flash, extremely brief and overwhelmed, gets lost in Jovian daylight. But a few hours later, a dark spot appeared at the cloud tops, like a bruise. Hubble, with its newly installed camera, recorded the evolution with clarity: a central mark, an expanding halo, texture details that no ground-based telescope could distinguish at the time. Then another fall, another spot, and so for days, Jupiter rotating every 10 hours and bringing the scars back into view, while teams coordinated schedules, pointings, and exposures. The visual climax came with one of the most massive fragments on July 18th. The images revealed a concentric bullseye, a dark central mark, a thin ring around it, and an expanding outer ring with dimensions comparable to Earth's diameter. The contrast exceeded, for a time, that of the Great Red Spot itself. It was easy to forget, faced with the geometric beauty, that this represented raw energy dumped into a deep atmosphere at tens of kilometers per second. In infrared, ground-based telescopes tracked residual heat growing and then cooling. With each passage of the scar through the field, the thermal peak shifted location, indicating how high-altitude winds redistributed material and energy. While Hubble mapped the marks on the day side, the Galileo probe, en route to Jupiter, gained the chance no one else would have to see one of the impacts on the night side without daylight interference. The sequences showed the flash igniting, growing, and fading in seconds. Later, the actual plume from an impact appeared escaping from behind the limb, at altitude far above the visible clouds, before falling back like chemical snow. This combination of viewpoints, space, ground, cruise orbit, transformed a unique event into a complete experiment. Initial flash, plume rise, ring expansion, mixing with winds, gradual disappearance. Chemistry told another part of the story. Ultraviolet and infrared spectra revealed the presence of compounds that don't usually show up in Jupiter's atmosphere, beyond the known ammonia and methane. Signs of sulfur and carbon-containing molecules, created or released under the extreme conditions of impact. It wasn't a permanent alteration. The planet's upper layers reshuffle quickly. But it was enough to map how a sudden injection of external material triggers reactions and redraws for weeks what we see at the cloud tops. Each day contrast changed, each rotation halo shapes distorted. Plumes, seen at different wavelengths, faded and spread. From an impact physics perspective, the gain was enormous. Previously, models depended on extrapolations, simulations of hot gas bubbles rising, estimates of where most energy would be deposited, guesses about the altitude where atmosphere would give way and plumes would reverse their ascent. In 1994, everything gained a measuring stick. The width of rings in the first hours, the speed at which outer halos grew, the interval to infrared thermal peak, the brightness decay time. Each of these numbers began anchoring models. And the planet, with its rapid rotation, helped by providing a natural time lapse. Just wait 10 hours to see the same scar under different illumination, different geometry, different scattering angle. The dynamics also became clearer. Jupiter isn't a block of still air, it's a tangle of jets and shear flows. Highly energetic plumes rose to the stratosphere, encountered fast winds, were stretched into ribbons and arcs, and descended elsewhere, drawing ellipses and crescents. Around some scars, waves formed analogous to those we see in a lake where a stone falls, except there the waves feel density variations and shear winds. This generated patterns resembling bullseyes, spirals, scalloped edges. By measuring how much each detail moved with each rotation, it became possible to infer high-altitude wind speeds and how different atmospheric layers talk to each other. The cultural impact was immediate. A year earlier, Hubble was the butt of jokes because of its factory optical problem. The repair mission corrected its vision, and suddenly the telescope delivered the most striking photos of the decade's astronomical event. Newspapers and magazines displayed the bullseye of the major impact. Textbooks incorporated the scars into planet mosaics. But the importance wasn't just imagery. By translating energy and dynamics into visible things, the event became a reference for calibrating scales. On Jupiter, most large projectiles die high in the atmosphere. Energy becomes compression and heat, much more than light. Seeing the flash, measuring the heat, and mapping the marks gave, for the first time, a coherent set of observables to compare with models. This sparked conversations beyond Jupiter. The idea of planetary defense was still young in the 1990s, and the impact sequence served as a reminder. Large objects exist, and gas giants swallow many of them. It's not that an earthly 1994 was likely. Earth has different gravity, different atmosphere, different neighborhood. But the basic physics of atmospheric entry is the same on any world. Knowing, for example, how energy deposition at high altitude triggers waves and plumes helps interpret smaller events like Chelyabinsk in 2013 and feeds models that estimate damage and explosion altitudes. Jupiter's case also accelerated surveillance networks. Years later, amateurs were ready to recognize new scars on the planet in 2009 and 2010. Triggering alerts that led professional observatories to respond within hours. There was also a lesson in celestial geography. The fragments hid a specific band of southern latitudes, determined by the orbit they inherited from the comet. This repetition facilitated honest comparisons between events, with similar atmospheric tracks from one impact to another. Differences in size and energy became more evident. In some falls, marks disappeared more quickly. In others, they persisted for months, crossing jet streams and beforming with each rotation. At the sequence end, a mosaic showed Jupiter speckled in the southern hemisphere, like a temporary atlas of scars. It's impossible to tell this story without returning to the cause, Jupiter's tidal force. In 1992, when the comet passed too close, the gravity difference between the planet-facing side and the opposite side broke the nucleus apart. The classical result of dynamics, a train of fragments, became, 2 years later, the sequence we observed. Each car had different mass. The smallest barely left traces, the largest produced rings that rivaled Earth in size. The interval between impacts reflected small velocity differences accumulated in the breakup. It wasn't blind luck, it was physics with a scheduled appointment. After the spectacle ended, the legacy remained. Data and a set of images that shaped planetary science. We learned that plumes can reach altitudes far above cloud tops, that high stratospheric winds paint halos in minutes, that chemistry responds quickly to external injection and then relaxes. We also learned to translate visual details into projectile energy and mass. And for astronomy's history, the episode consolidated Hubble as a high-definition tool for rapid phenomena. The turnaround it needed after the repair. If you had been in the control room that week, you would have felt a curious routine. Wait for the predicted impact time, check if any flash was recorded by the infrared team or the space probe, wait for Jupiter to rotate, position Hubble for when the impact latitude enters the field, photograph, measure, archive. Repeat the cycle with the next fragment. Science there was less rare click and more disciplined marathon. Each planet turn offered a new page, and it was this repetition that allowed seeing pattern where before there had only been theory. 3 ideas after everything help retain the essential. First, the comet wasn't bad luck, it was classical dynamics, capture, tidal disruption, serial impact. Second, what we saw with Hubble and Galileo became a ruler for impact physics in deep atmospheres, flash, plume, rings, chemistry, winds. Jupiter, besides being a powerful laboratory, serves a practical role in the solar system, absorbing projectiles that could continue onward. The combination explains why that week in 1994 remains present in classes, books, and documentaries. For the first time, collision stopped being abstraction and became an observed, measured, revisited sequence. If a new Shoemaker-Levy appears, we'll have even better instruments, mature adaptive optics on large ground telescopes, space observatories sensitive to infrared and ultraviolet, cameras covering the entire planet minute by minute. But the logic will follow what we learned there: predict, point, wait for rotation, repeat, compare. That's what transformed a spectacular event into solid knowledge. In 1994, we watched Jupiter take a beating. Since then, we better understand what that beating means for it, for us, and for the solar system's dynamic history. The Carrington Event in 1859 was the largest solar storm ever recorded. If it happened today, it could cause global blackouts and satellite damage. The Carrington Event in September 1859 was a solar storm so intense it remains a benchmark to this day. On the morning of September 1st, British astronomer Richard Carrington observed a sudden flare in a sunspot region, an extremely rare white flash, independently recorded by Richard Hodgson as well. Hours later, Earth began feeling the effects. In less than a day, a coronal mass ejection, a magnetized cloud of plasma, crossed space and struck our magnetosphere at exceptional speed by solar standards. The result was a geomagnetic storm that dominated September 1st and 2nd, the strongest since instrumental records began. Auroras exploded at improbable latitudes, telegraphs sparked, operators got shocked. In some areas, they disconnected batteries and continued transmitting using only electricity induced by geomagnetic currents, a testament to the event's violence. This story has a prologue. Days earlier, around August 28-29th, initial solar activity had already lit up skies and swept part of the solar wind ahead of Earth, preparing a clear path for the following impact. When the main ejection departed the Sun, it encountered fewer obstacles and arrived in about 17 to 18 hours, much faster than the usual 2 to 3 days. This preconditioning helps explain why the storm was so extreme. Magnetic readings at observatories like Kew in England recorded off-the-charts variations. Modern estimates place the storm index, DST, at record negative values. The nickname Carrington Event came later, honoring the observer of the flare. What happened on the surface? Auroras were seen far beyond the polar circle. Documented reports from Mexico, Hawaii, Japan, Australia, and even Colombia, so intense that people could read newspapers at night, according to period newspapers. Simultaneously, telegraph lines in Europe and North America failed, insulators cracked, paper burned at stations, messages traveled with batteries disconnected, powered by the sky itself. It's a collection of scenes that concretely shows how currents induced in long cables and ground can escape human control when the storm is large enough. Now, the parallel with today. The underlying physics is the same. The Sun launches particles and fields, Earth responds. The difference is our technological dependence. Our telegraph lines are now transmission lines hundreds of kilometers long. Satellite networks, GPS, submarine cables. An 1859 scale storm could pressure each of these layers through well-known pathways. Let's start with the electrical grid. When Earth's magnetic field fluctuates rapidly, extremely low-frequency currents emerge, seeking easy paths, rocky crust, seas, and especially long high-voltage lines. These geomagnetically induced currents, GIC, saturate transformers, steal reactive power from the system, and trigger protections. On March 13, 1989, a storm far less extreme than 1859's brought down Hydro-Quebec's grid in 90 seconds, leaving the province dark for 9 hours. Since then, utilities have installed compensators, revised settings, created operating procedures for storm times, but risk remains, especially in high-latitude regions with very extensive lines. Satellites would come next on this impact list. Energetic particles and varying fields electrify surfaces, damage sensitive electronics, contaminate measurements. The upper atmosphere also heats up and swells, increasing drag on low satellites. In 2022, a moderate storm caused dozens of newly launched Starlink satellites to re-enter and burn up because they couldn't overcome the additional resistance from rarefied but denser than predicted air. In May 2024, during the first G5 storm since 2003, NOAA reported extreme disturbances. Auroras reached the tropics, satellite services degraded, and even GOES 16 transmission was intermittent for hours. In a Carrington-class scenario, we'd have many simultaneous anomalies, blind sensors, resets, attitude control loss, and rapidly decaying low orbits. Satellite navigation, GPS, GLONASS, etc., would suffer from two sides: ionospheric scintillation, which makes signals flicker and changes travel time, and atmospheric model errors. This disrupts precision agriculture, financial and telecom network synchronization, drones, and airport landings that depend on fine corrections. In commercial aviation, especially polar routes, HF radios could go silent for hours, forcing expensive diversions. These effects already appear in strong storms. In something 1859 scale, they'd be the rule, not the exception. Records from 2003 and 2024 help calibrate this picture. There's also the physical internet, submarine cables that stitch continents together. A 2021 study highlighted repeater vulnerability, the active equipment every few dozen kilometers that keeps signals alive underwater. They're connected by long conductor stretches and can suffer from induced currents and out-of-spec voltages. It's not that the internet ends, but it's plausible to imagine digital islands, local networks operating, intermittent oceanic crossings. For distributed databases and global services, this means slowdowns, crashes, and cascading reconnections. How would this movie begin on a contemporary Carrington day? First, the Sun. Observatories like SDO, SOHO, and Stereo would see a very bright eruption, and coronagraphs would show a wide, fast coronal mass ejection with possibly southward-oriented field, the most effective orientation for coupling energy to Earth's field. We have some warning, hours with the ejection itself being seen, and then tens of minutes, when the shock wave and solar wind reach a sentinel at L1 point, like DSCOVR. With readings, centers like NOAA's SWIPC issue G4, G5 warnings. In May 2024, this alert flow worked. The first G4 watch in nearly 20 years was issued, followed by G5 warnings as ejections arrived in waves. On Earth, power operators would reduce loading on long lines, activate reactive compensation, change topologies to shorten GIC paths, and monitor vulnerable transformers, measures motivated by standards like NERC TPL 007, which require planning systems for severe geomagnetic events. Still, in rocky regions, poorly conductive soil, and extensive grids, we'd see alarms, local outages, perhaps regional blackouts. The difference from 1859 is response capability. Today there's telemetry, simulations, and a preparedness culture born with Quebec 1989 and matured since. In the skies, satellite operators would put spacecraft in safe mode, rotate panels to reduce differential charging, limit maneuvers, and revise low orbits to compensate for extra drag. LEO constellations could lose hundreds of meters of altitude daily. Anomalies would multiply, but many would be transitory. The 2012 experience, when an almost Carrington passed 9 days away from Earth alignment, shows what's at stake. No one was in the path, but stereo data analysis indicated a direct hit would have been very serious for grids and satellites. In 2024, we've already seen that even robust satellites can suffer temporary transmission blackouts mid-storm. At the user level, symptoms would be familiar and widespread: erratic GPS, jumping maps, drones losing position, silent HF radios at high latitudes, auroras appearing where they don't belong, aurora prediction apps turning red, and in worse cases, localized power outages. Would it be the end of the world? No. It would be a prolonged stress test with waves of disturbance as different ejections arrived hours apart, and a reminder that the sun sets the pace on scales we sometimes forget. To put this in perspective, comparisons help. The March 1989 storm, DST, around -589 NT, brought down a major electrical grid, damaged transformers, and caused dozens of satellite anomalies. The October 2003 sequence, the Halloween storms, brought record flares and a flood of warnings. In May 2024, we had a G5 that brought auroras to tropical latitudes and revealed bottlenecks, including a geostationary weather satellite going silent for hours. The Carrington Event went beyond. It traveled fast, preconditioned, and showed what the Earth-Sun system can do in extreme mode. These benchmarks together form the ruler we use to measure risk. What have we learned since 1859? That observation matters. Today, the space weather community lives on continuous monitoring, models that incorporate ground profiles, which dictate induced current intensity, operating patterns that adjust to sun weather, and resilience engineering in substations and satellites. Some standards, for example, require planning against a reference event and demand transformer vulnerability studies. It's no guarantee, but it's a cushion. Research has also advanced into less visible domains like submarine cables, proposing mitigation and route redundancy. And public alerts from NOAA, ESA, and others have gained clear language so operators and the public understand what to expect hour by hour. If tomorrow we had a Carrington repeat, the likely script would be instability, not collapse. Nights with auroras where there aren't any, alarms sounding in control rooms, some blackouts, repairs, transformer replacements, satellites entering and exiting safety modes, re-entry speeds reassessed, certain global services slower, aviation diverting from polar routes, amateur radio silent in certain bands, and degraded navigation at scales that bother agriculture and logistics. And after the peak passes, a queue of reports, adjustments, and lessons learned, like in 1989, 2003, and 2024, just amplified. What changes with this understanding is that in 1859, copper lines sparked without protection. Today, entire grids can breathe differently for a few days to weather the storm. The sun hasn't gotten tamer, we've just learned to listen. The cosmic microwave background is the thermal echo of the Big Bang. The cosmic microwave background is literally the leftover glow from the beginning of everything. This isn't a metaphor, it's real light, spread across the entire sky, coming equally from all directions, a glow so cold and gentle that our eyes can't see it. It's now in the microwave range and has a temperature of about 2.7 Kelvin, just above absolute zero. We call this the thermal echo of the Big Bang because it's the light that filled the universe when it was hot, dense plasma, and which has been stretched by expansion until it became this frozen whisper that passes through antennas, radio telescopes, and even, barely, old television sets. To understand where this echo came from, we need to go back to the first chapters when the universe was truly young. In the first moments, everything was so compressed and hot that matter and light lived stuck together. Electrons, protons, and photons formed an opaque soup. Light tried to move, but hit free electrons at every step and couldn't travel far. Think of fog so thick that car headlights only illuminate a white blur. Hundreds of thousands of years pass, the universe expands, cools. There comes a moment when temperature drops enough for protons and electrons to unite into hydrogen atoms. It's the instant when the fog lifts. Without so many free electrons in the way, light stops being scattered all the time and can travel freely. From there, photons traveled essentially in straight lines, crossing the cosmos for billions of years. This liberated light is what we measure today as the cosmic microwave background. When it broke free, this light had a yellowish glow, typical of something at about 3000 Kelvin, the temperature of an old light bulb filament. But the universe didn't stop. It kept expanding, and expansion plays a trick on any wave. It stretches its wavelength. This is what we call redshift. Over 13.8 billion years, those photons were stretched like a rubber band. Color shifted from visible to infrared and then to microwaves. Energy decreased. The temperature of this light dropped. What was a bright flash became an almost silent background, with the tone of a black body at 2.7 Kelvin. When we say it's a thermal echo, that's what it is, the heat signature of the baby universe, cooled and stretched by expansion. For a long time, this idea was just a prediction. The Big Bang model said this radiation should exist, cold and uniform, with the exact spectrum of a black body. In the 1960s, two engineers, Arno Penzias and Robert Wilson, were working with a large microwave antenna and encountered persistent noise coming from all directions, day and night, winter and summer. They cleaned the antenna, evicted pigeons that had nested there, checked all cables. The noise remained. Across town, a group of physicists had published the prediction. If the Big Bang is right, there should be a frozen cosmic glow in microwaves. The pieces fit together. The detection of the cosmic microwave background was born. It was 1965, and the universe had just confessed its infancy. One of the most impressive things about this radiation is how perfect it is. When we measure its spectrum, the amount of light at each frequency, we find the smooth, precise curve of an almost ideal black body. It's the best approximation of a black body humanity has ever measured in nature. This matters because it says that light was indeed in thermal equilibrium in the remote past, as if the universe had been a great homogeneous furnace. It's exactly what the Big Bang predicts for the hot, dense plasma phase. In other words, it's not just any glow, it's the right glow. But the real universe isn't perfectly smooth. If it were, there would be no galaxies, stars, people. There needed to be some relief, however tiny, in density and temperature in that primordial sea, small ups and downs that gravity could amplify over time. In the first microwave sky maps, this relief didn't appear. The background was too uniform, to 1 part in 10,000. Sensitivity was lacking. In 1992, NASA's COBE satellite showed irregularities for the first time. Temperature variations of about 1 part in 100,000 scattered across the sky. They weren't visible spots like a cloud. They were small differences, like the almost imperceptible texture of fabric when you run your hand against the light. The community was thrilled. There was the embryo of structures. Years later, with the WMAP and then Planck satellites, these maps gained incredible resolution and precision. We began seeing the microwave sky as a finely stippled mosaic, and each dot holds information about the universe when it was only 380,000 years old. What are these spots, anyway? They're not objects. They're regions slightly hotter or cooler than average. In the primordial plasma, gravity tried to pull matter together in slightly denser regions, while light pressure pushed outward. This push and pull generated sound waves, yes, sound, though nothing like sound in air, that propagated through the plasma. Where the wave was compressed, temperature and density were higher. Where it was rarefied, lower. When the fog lifted and light was liberated, this pattern was stamped on the radiation, like when you freeze the surface of a choppy lake and see the wave pattern. Today, when we analyze the typical size of spots and how they're distributed, we're literally hearing the music of the baby universe and reading in it the score of cosmological physics. There are two map details worth a separate look. The first is a large gradient called the dipole. Radiation appears slightly warmer in one sky direction and slightly cooler in the opposite direction. This isn't a trace of the primitive universe, it's the effect of our velocity. Since Earth and the Sun and the Milky Way move relative to the background, we experience a slight microwave headwind from ahead and thin air from behind. It's the same principle as a siren sound changing pitch when it passes you. By measuring this dipole, we know how fast we move relative to the cosmos's rest frame. The second detail is polarization. Background light carries not just temperature, but also a subtle pattern of electric wave orientation. This pattern, generated by light scattering off the plasma's last electrons, brings extra clues about primordial sound waves and about the path light traveled, being slightly deflected by structure gravity, an effect called weak lensing. With temperature and polarization maps, the picture becomes panoramic. We can follow light's path from the surface of last scattering, the moment fog lifts, to us, passing through all the deviation structures made in the sky's appearance. This sum of information allows, for example, measuring how much matter exists between there and here through how much it distorts the original pattern, or dating when first stars ignited because they reionized gas and left their signature in how background light was polarized. Beyond the big picture, the microwave background became a working tool for asking specific things about today's universe. When this light crosses a galaxy cluster bathed in hot gas, photons can be kicked to slightly higher energies in collisions with electrons, an effect named after Sunyaev and Zeldovich. Seen on the map, the cluster draws a peculiar shadow. With this, we can count clusters in large sky areas and test, independently, how matter has clumped since the beginning. In another shortcut, the background pattern itself is slightly wrinkled by the cosmic web's weight, a type of weak gravitational lensing. By measuring this distortion, we reconstruct mass distribution along the line of sight. Again, the microwave background is simultaneously ancient photograph and current flashlight. Why is this radiation such strong proof of the Big Bang? Because it unites three pieces that separately would be easy to doubt. First, the existence of microwave glow coming equally from all directions. Second, the fact that this glow has the spectrum of an almost perfect black body, as expected from a universe that was once plasma in equilibrium. Third, the presence of small variations with the right intensity and distribution for an expansion picture with matter, radiation, and nearly random initial fluctuations. Any serious alternative to the Big Bang would need to explain these three things at once and with the same precision. To date, no competitor has appeared that does this better. This doesn't mean everything is solved. The microwave background itself participates in major open questions. One is tension around the universe's current expansion rate. Measuring cosmic rhythm in different ways, near us with supernovas and galaxies, and far away via microwave background and its model, we get numbers that don't coincide perfectly. It could be just technical detail. It could be a clue to some new physics, some model ingredient needing adjustment. Another front is searching for a special type of polarization called primordial B mode, which would be a trace of gravitational waves generated in the universe's first moments in an extremely accelerated expansion process known as inflation. It's an extremely difficult measurement because dust from our own galaxy mimics the signal. We haven't seen this trace convincingly yet. If we do someday, it will be like hearing the universe's birth crack. Even without entering these technical details, what the microwave background has already given us is extraordinary. It's rare in science to have an experiment that looks directly so far back in time with such clarity. In astronomy, almost everything is deduced indirectly. You observe stars and galaxies and reconstruct history. Here, we literally see the universe at 380,000 years old, not in a photo of a galaxy, but in a backdrop that surrounds us on all sides. It's as if we were inside a sphere whose inner wall holds the portrait of the cosmos's infancy. This portrait is what we lovingly call the surface of last scattering. It's not a physical wall in space, it's a limit in time. Looking farther means looking earlier. Before that age, fog was too dense for light to travel, so there's no way to capture older photons from there. To cross that veil, we'd need messengers that don't interact so much with matter, like neutrinos. And there is in fact a predicted neutrino background, much harder to capture. The microwave background, therefore, is our photographic horizon. A curiosity that helps feel the signal's reach. A tiny fraction of the static you'd see on an old TV, out of tune, was precisely the microwave background. That snow on screen came from many noise sources, but a handful of percent was the universe drinking its own light. Today, without that analog technology, the metaphor lost its everyday example, but the principle remains. Microwaves are everywhere, passing through thin walls, detected by radio antennas and very sensitive sensors, cooled to very low temperatures, on satellites and stratospheric balloons. It's a weak but persistent signal, easy to miss if you don't know what to look for, impossible to ignore when you tune the right instrument. Over 3 decades, precision increased to the point where we see small statistical oddities that generate discussion. Some discuss a cold spot more extensive than expected in one sky region. There are debates about large-scale alignments that might just be coincidence. There are fine comparisons between what the microwave background says and what galaxy surveys confirm. This is how science progresses, fraying the limits of what's been measured and trying to decide whether a ripple outside the pattern is noise, chance, or clue. Whatever the answer, the core of the picture, the thermal echo, its spectrum, its main ripples, is solid. Finally, it's worth returning to the opening image, that of an echo. The analogy works because the universe, in expanding, let the thermal memory of that primordial plasma resonate. The sound waves it plays are frozen in the spot pattern. The general tone of that sound became cold microwaves. And to complete it, the echo itself is useful in 2 ways, as a portrait of the past and as a ruler of the present. With it, we measure sizes, count times, weigh invisible components, test physics laws, and look for deviations. Enceladus, Saturn's moon, has water jets that indicate subsurface oceans. Enceladus is small on paper, just over 500 kilometers in diameter, but what happens there is too big to go unnoticed. Near this Saturn moon's south pole, long, nearly parallel fractures, the tiger stripes, spew jets of water vapor and ice, like geysers. It was the Cassini probe that, in 2005, showed this activity in detail and connected the dots. The jets feed Saturn's E-ring with ice grains launched into space. The discovery repositioned Enceladus on the map of best chances for finding habitable environments in the solar system. When you see a water jet coming out of ice, the first question is obvious: where does this water come from? Cassini answered in stages. First, gravity measurements made by passing close to the moon revealed something soft beneath the crust, a body of liquid water, not just in a local pocket, but extensive enough to affect the gravitational field. Then, a fine detail of rotational motion, a wobble called libration, appeared too large for a completely solid body. Putting the 2 lines together, the conclusion gains strength. Enceladus has a global ocean under its ice shell. But how does such a small world maintain a liquid ocean? The answer is tidal heating. Enceladus is in orbital resonance with Dione, another Saturn moon. For every 2 orbits of Enceladus, Dione completes 1, and the gravity of Saturn and its neighbor stretches Enceladus's orbit a bit. This periodic push and pull deforms the interior, generates friction and heat, enough to keep liquid water at the contact between the rocky core and the ice base. The effect isn't weak. Just the Tiger Stripe region alone adds up to several gigawatts of heat, and Cassini thermal maps showed spots much hotter than expected for such a cold surface. Ice gets thinner at the South Pole, and there heat finds a way to escape as vapor and particles. This ice thickness varies. Models with gravity and topography data suggest tens of kilometers on average, but possibly just a few kilometers at the South Pole, precisely where jets merge. This explains why Enceladus's plumbing concentrates there. Fractures connect the ocean to the exterior and function as valves. With each tidal stretch, cracks open a bit, pressure rises, and the moon releases more vapor and ice. When the tide loosens, activity decreases. It's a mechanism that fits well with observed variations. What Cassini did then was pass through the plume to smell and taste what came out. Two instruments were decisive: the mass spectrometer, INMS, which sucked up gases, and the dust analyzer, CDA, which captured ice grains and melted these tiny samples to see their components. The chemical portrait is one of the most exciting in planetary exploration. Besides water, there's carbon dioxide, methane, and a key ingredient, molecular hydrogen, strong signal of reactions between hot water and rock at the ocean bottom, like we see in hydrothermal vents on Earth's ocean floors. In 2015, the team also identified silicon nanoparticles, which form when very hot water, something like tens to over 90 degrees Celsius, interacts with rock and then cools. And in 2018 came complex organic molecules with dozens to hundreds of atoms, building blocks that, on Earth, life's chemistry loves to manipulate. An essential element was missing to complete the habitability menu: phosphorus, which enters DNA, cell membranes, and ATP, life's energy currency. In 2023, a deep analysis of ice grains pointed to sodium phosphates in surprising abundance in plume samples, potentially up to 100 times more than in Earth's oceans. This isn't proof of life, but it's huge news for any microbe that might hypothetically exist there. The ingredient kit is on the table. Meanwhile, telescopes orbiting Earth continue monitoring Enceladus's smoke from a distance. In 2023, the James Webb Space Telescope detected an absurdly extensive plume, thousands of kilometers long, and managed to see how this material feeds not just the E-ring, but parts of Saturn's environment as a whole. On a moon scale, it's like opening a faucet and seeing the whole neighborhood change. The image is useful for a practical reason. It shows that activity isn't an occasional sneeze, it's a sustained process with environmental impact. Put it all together, and the picture becomes clear. Enceladus offers three things astrobiologists always ask for: liquid water, chemical energy, and essential elements. Water, a global ocean under the ice. Energy, hydrogen generated by water-rock interaction, exactly the type of fuel microbes use in terrestrial hydrothermal vents. Elements from carbon and nitrogen to phosphates, including complex organic compounds. Missing is the forbidden word, life, because we haven't seen anything only an organism would produce. But from a where to look first perspective, few flags are so green. And yes, Enceladus is small. This has enormous practical advantage for the future. It's relatively easy to enter orbit and even land. That's why the most ambitious plan on the drawing board is the Orbalander, a flagship-class mission which would first orbit the moon for over a year, sampling the plume repeatedly, then land for 2 years of surface science, carrying instruments designed to search for biosignatures directly in freshly fallen particles. This mission's priority was recognized by the scientific community in the most recent decadal survey as the decade's second biggest new bet. The first is a mission to Uranus. There's no scheduled launch date, but the idea is mature and has strong backing. It's the type of mission that could, with luck and rigor, transform Enceladus from promise to answer. Let's step back to understand the tiger stripes. These four main fractures, aligned almost parallel, are the mouths of the plumbing system. Cassini measured temperatures above expected along these lines, with localized peaks, as if hot spots marked openings where heat and water rise. Heat distribution is a beautiful puzzle. Thermal and flow models suggest that fresh, porous snow falling back insulates the surface, while heat comes from below, and multiple fractures per stripe help explain the observed pattern. None of this would be visible without the contrast between the ultra-cold surrounding crust and the warm grooves where the ocean breathes. Another important piece is the E-ring, Saturn's widest and most diffuse ring. It's basically Enceladian snow scattered through orbit. Part of what leaves the moon falls back as fine snow, part escapes and becomes the ring. Ultraviolet observations and particle counts showed the plume flow is sufficient to continuously replenish the ring. Enceladus isn't just an active world, it's a world that paints the planet around it. And what's beneath the ice? Data points to a porous, rocky core in contact with ocean water. There, at the rock-water interface, chemistry comes alive, figuratively speaking. When water percolates through mineral-rich rocks and heats up, reactions occur that release hydrogen and alter pH. Exactly the scenario that, on Earth, feeds entire ecosystems on the seafloor, independent of sunlight. The silicon nanoparticles and H2 in the plume are tickets that rode up the fracture elevator and tell us this chemical plant is running. The H2 detail matters because it's food for methanogenic microbes. The silica detail matters because it requires hot water touching rock. To complete the habitability circuit, phosphorus was indeed missing, and it appeared in ice grains as phosphates, exactly the form terrestrial organisms use. A caveat: having ingredients isn't having a ready recipe. Phosphate presence says the pantry is stocked. It doesn't say if someone's cooking. That's why sampling particles directly with instruments designed to detect biological patterns like specific imbalances, fractionated isotopes, polymers with certain signatures, is the logical next step. Even without landing, there's much to learn just from more orbits and flybys. James Webb itself, by measuring such a large plume, helps calibrate how much material Enceladus loses, how flow varies, and how this connects to tidal cycles. This in turn feeds models that say whether the ocean is stable for ages, great for life to mature, or something intermittent, harder but not impossible. There are signs that tidal heat production can be sustained for very long times if certain resonance locks with Saturn are maintained. Good news for those rooting for constancy. A doubt that always comes up is, what if it's just ice heating up on top, like surface spray without an ocean? This hypothesis was considered early on, but accumulated data knocked down the idea. Global wobble requires decoupling between shell and interior. Gravity demands a liquid layer. Concentrated heat and fractures and chemistry require water touching rock. All this points to an ocean connected to the outlets. Unlike just melting ice locally, the pictures of a world with internal circulation, where water rises and falls, exchanges heat and matter with the bottom, and breathes through cracked skin. It's also worth calibrating expectations. Signs of life aren't synonymous with critters in photos. What's sought first are chemical signatures difficult to produce without metabolism, patterns in organic chains, strange isotopic relationships, compound combinations that, in practice, only appear when something living is rearranging matter. Even so, final proof requires care. Geological processes can mimic biological signals. Contamination can deceive. Weak statistics can induce error. Enceladus's merit is reducing technical difficulties. The sample is already being ejected for free into space without needing to drill tens of kilometers through ice. In the big picture, Enceladus became an astrobiology laboratory. It lets us test ideas about how life could arise and sustain itself without sunlight, just with chemistry and internal heat. It allows comparing a global ocean under ice with terrestrial environments like ocean ridges and alkaline vents. and it still converses with other ocean worlds like Europa at Jupiter and Triton at Neptune, composing a theme that's probably common in planets and moons: hidden water, protected, heated by tides. Enceladus is special because in it, water rises to tell us what it saw. If in a few years an Orbilander mission lands there, the sequence will be roughly like this. First, orbit to precisely map fractures, measure plume flow in different tidal phases, and collect particle samples without haste, repeating to gain statistics. Then land near a tiger stripe, extend instrumental noses and tongues, and continue collecting, this time without flyby velocity. In both modes, the question is direct. Are there chemical patterns that only life explain economically? The moon that today paints a ring might also paint the most desired answer in space exploration. For now, science continues pulling the thread with what we already have. Each new data set, gravity, rotation, heat, chemistry, reinforces the narrative of a global ocean, hot at the bottom, ventilated by fractures, rich in ingredients. Cassini showed us the geysers and tasted the soup. James Webb revealed the plume's dimension and its influence on Saturn's system. Phosphorus studies closed an important gap in the menu. It's rare for such a small world to carry so much consequence. On Enceladus, what's missing isn't motivation, it's the next visit. Einstein's theory of relativity predicted the existence of black holes before any evidence. Today, it's easy to think of black holes as cosmic celebrities, images of glowing rings, gravitational waves ringing like bells, stars spinning like fireworks around an invisible center. But for many decades, they were nothing more than a logical ghost that emerged from an equation. Albert Einstein's general theory of relativity, published in 1915, predicted the existence of these extreme objects long before any observational evidence. This is the story of how a purely theoretical idea, born from mathematics, became one of the pillars of modern astronomy. Let's start with the change in perspective that relativity brought. Before it, we thought of gravity as a pulling force, like a magnet. Einstein proposed another image. Gravity is the curvature of space and time. Matter and energy deform the fabric of space-time, and everything, light included, follows the lines of this curve. It's not literally a rubber mat, of course, but this metaphor helps. Where there's mass, the mat sinks. Where the sinking is extreme, possible paths for anything will inevitably turn inward. It's in this logic that black holes appear, regions where the curve is so strong that, past a certain edge, not even light finds an escape route. 1 year after Einstein published his equations, in 1916, physicist Carl Schwarzschild found the first exact solution for the simple case of a spherical, stationary mass. From the World War I front lines, he sent the solution. It had a special surface, defined by a certain radius, beyond which mathematics said light could not escape. Today we call this limit the event horizon, and the associated size the Schwarzschild radius. At the time, however, almost no one thought this described something real. It seemed like a coordinate trick, or an ugly phase of mathematics that nature would avoid. Albert Einstein himself had reservations. In 1939, he published a paper suggesting that complete collapses might not occur in nature. There was more skepticism than enthusiasm. Meanwhile, another branch of astrophysics gave a silent push. Understanding how stars support their weight revealed their destiny. They don't burn wood, they fuse nuclei, generating outward pressure. When fuel runs out, gravity wins. The question is, how far? In the early 1930s, Subramanian Chandrasekhar showed that white dwarfs cannot have arbitrarily large mass. There's a limit beyond which they collapse. The discussion was heated, but the message was given. Some stars end as something denser. Soon came ideas of neutron stars, Bode and Zwicky, and shortly after, the decisive calculation. In 1939, J. Robert Oppenheimer and Hartland Snyder showed that if a massive star exceeds certain limits, gravitational collapse proceeds without break. Space-time itself closes the exit paths. They didn't use the expression black hole. It would only be born decades later, but described in so many words the birth of the event horizon. It was a clean, technical prediction that fell into a world on the eve of war. The subject stayed quiet for quite a while. The theory, however, continued to mature. New solutions to Einstein's equations appeared. In 1963, Roy Kerr found the solution for a rotating mass. This detail changes everything. Realistic black holes rotate. Rotation drags space around, as if spacetime's very fabric were pulled along. An outer region called the ergosphere emerges, where nothing can stay still. Everything is dragged. In these scenarios, physics predicted curious effects, like the possibility of extracting energy from a spinning black hole through processes that manipulate the dragged region. At the same time, theorems about horizon area and no hair, the idea that black holes are simple, described only by mass, rotation, and electric charge, gave unexpected elegance to the theory. On paper, this zoo of possibility seemed consistent and even beautiful. In the sky, nothing for now. The turnaround required new observation windows. In the 1960s, radio telescopes and X-ray sensitive instruments began revealing a sky invisible to the naked eye. Suddenly, absurdly luminous and compact objects appeared, quasars, active galactic nuclei that shine brighter than entire galaxies, powered by what? The hypothesis of gas disks falling into supermassive black holes gained strength because relativity predicts tremendous efficiency in this process. Spiraling inward, gas heats to extremely high temperatures and converts a notable fraction of its mass into radiation. In 1971, a more domestic candidate appeared, a system in our galaxy, Cygnus X1, with a normal star orbiting a very heavy invisible companion that emitted X-rays from a hot disk. There was no surface to stop the fall. Everything matched a stellar black hole. Gradually, skepticism lost ground. Notice the logic. No one sees the black hole because it doesn't emit light. What's done is observing predictable effects of relativity. Weird orbits, ultra-energetic light from falling gas, narrow jets spat out at near light speeds that emerge from the poles, like galactic lighthouses. Such jets, incidentally, are frequent in fast-spinning black holes. Magnetic fields channel part of the gas's energy, and possibly the black hole's own rotation, building particle cannons that cross galaxies, another prediction nature seems to have embraced. While multi-wavelength astronomy grew, relativity's precision clock continued on another front, the movement of stars near our galaxy center. In the 1990s, two teams began tracking, year after year, stars describing very tight orbits around an invisible point in the Milky Way's heart. One of them, called S2, completes a revolution in about 16 years and at periapsis reaches a significant fraction of light speed. The math is straightforward. To keep such a star in such a small orbit, the mass concentrated there needs to be millions of suns, and it needs to be crushed into a volume smaller than the solar system. There's no ball of stars, no cluster of stellar remnants that could hold together without break or apart. The only consistent candidate is a supermassive black hole, what we now call Sagittarius A star. But the iconic confirmation, the one that jumped into pop culture, came in 2015 and 2019. In 2015, giant antennas on two continents heard for the first time the rippling of space-time when two black holes merged over 1 billion years ago. Gravitational waves, predicted by Einstein in 1916, arrived as a chirp that lasted less than a second, carrying information about masses and rotations in its timbre. It wasn't just an effect of gravity, it was the sound of curvature itself oscillating. In 2019, a global consortium of radio telescopes functioned as an Earth-sized antenna, and recorded the shadow of the black hole at the center of galaxy M87, a ring of light distorted by gravity with a hole in the middle. The image matched the size and shape predicted by general relativity for a black hole of that mass. In 2022, the same method revealed the shadow of our central neighbor, Sagittarius A star. It was the visual signature of the event horizon, the boundary predicted more than a century before. If we put all these pieces together, the timeline becomes clear. First came the theory, Einstein's equations, Schwarzschild solution, generalization for rotating objects, theorems about collapse and simple black hole interiors. Then came stellar physics, saying some have violent endings, stability limits, collapse scenarios, possibility of dense remnants that go beyond white dwarfs and neutron stars. Next, observational clues, compact X-ray sources, quasars and jets that demand powerful engines, stars spinning around something invisible and massive, gravitational waves, the direct shadow of the horizon. In 1916, all this fit in a few lines of a mathematical solution. By the mid-20th century, it was the subject of theoretical debates. From the century's end onward, it became an inventory of data. It's worth slowing down here and returning to the original question. Why say that relativity predicted black holes? Because the essential features were, from the beginning, embedded in Einstein's game rules. A black hole is the natural consequence of taking curvature to its ultimate conclusion. If you take a sufficiently compact mass, spacetime's very structure around it alters so that all possible paths point inward. This is a statement about geometry, not about force. And from this geometry follows a coherent list of effects. The horizon as a no-return boundary. Extreme time delay, measured by a distant observer when something falls. Redshift of everything trying to escape. Light's orbit in an unstable ring outside. The size of shadow a black hole projects against surrounding gases glow. When images and measurements began accumulating, they matched this list. It's true the story wasn't linear. There was skepticism, including from Einstein himself at certain moments. And there were alternative versions trying to save stars from total collapse. There were even those who preferred talking about frozen stars or stalled collapses, as if nature always found a way to avoid the abyss. Time, however, tied up loose ends. Rotating solutions explained well the jets and energies of active nuclei. Stellar orbits at the galactic center left no room for exotic clusters. Gravitational waves brought a new laboratory, breaking the argument that you'll never see the final dance. And shadow images consolidated with a photograph what mathematics had drawn. Along the way, physics gained even more depth. When Stephen Hawking calculated in the 1970s that black holes should emit very weak thermal radiation through quantum effects, he scrambled the boundary between relativity and quantum mechanics. Objects that, classically and perfectly, would let nothing escape, begin to leak slowly over immense times. On human scales, this doesn't change the functioning of astrophysical black holes. They're too giant and cold to evaporate appreciably. But the idea opened a conceptual portal. Understanding black holes might mean understanding as a bonus how to join the two great physical theories of the 20th century. Even this, you notice, springs from ground inaugurated by Einstein. And why did the prediction come before the evidence? Because general relativity is a high-reach theory. It wasn't made to explain black holes, it was made to explain gravity. If the basic rules are correct, extreme cases are inevitable. Sometimes nature takes time to offer us a window. X-ray sensitivity was lacking. Technique for measuring gravitational waves was lacking. Resolution for seeing shadows was lacking. As soon as windows opened, theoretical characters began appearing on stage. You might reasonably want a final picture. What exactly did theory say and we confirmed? It said compact masses curve spacetime such that a no-return boundary exists. We confirmed the boundary by measuring shadows, and the gravitational wave chirps when horizons merge. It said time runs differently near intense fields. We see lights shift and the slower blinking of processes near the horizon. It said spiraling gas heats and shines very efficiently. We see hot disks radiating from X-rays to radio. It said rotating objects drag spacetime. We see drag signatures in pulsars, satellites, and gas behavior around active nuclei. Broadly, theory speaks, the sky responds accordingly. In the end, the trajectory of prediction before proof isn't accidental. It's the mark of a powerful theory. Einstein's equations already carried in their DNA the possibility of horizons and total collapses. Our technological arsenal lacked the capacity to look at the right places with the right instruments at the right frequencies. The 20th century solved the experimental difficulty step by step. The 21st century is transforming black holes into words, into numbers, masses measured to 2 decimal places, estimated rotations, images compared pixel by pixel to relativistic simulations. Today we know that supermassive black holes exist at the center of most galaxies. Today, when we look at a galaxy, we don't see just an archipelago of stars. We know that there, at the center, lives an extreme object, a supermassive black hole, millions to billions of times the sun's mass, silent when it lacks food, furious when fed with gas and dust. The key phrase is this: today, we know that supermassive black holes exist at the center of most galaxies. And it's not an elegant guess, it's a conclusion built over decades, adding different clues that, together, tell the same story. The turning point begins when astronomy learned to measure movements precisely near galactic nuclei. If you track the dance of stars and gas in a galaxy's core, you can weigh what's at the center. That's how it works with our Milky Way. For years, teams observed stars making tight curves around a dark point. One of them, called S2, completes a revolution in about 16 years, and at closest approach, reaches an appreciable fraction of light speed. Do the simple gravity calculation. To maintain such tight, fast orbits, the central mass needs to be millions of suns, compressed into a volume smaller than the solar system. There's no cluster of stars or exotic objects that could withstand this compaction without falling apart. The remaining candidate is the supermassive black hole, in our case, Sagittarius A*, with something around 4 million solar masses. This dance method repeats in other galaxies, sometimes with gas instead of stars. Rotating gas emits light with a velocity stamp. Doppler effect. One side shifts toward blue, the other toward red. In some rare cases, there's even a natural laser ruler. Water molecule clouds act as masers, nature's version of a laser, and trace a thin disk around the center. The geometry of these masers allows measuring rotation with absurd precision, and the result again points to a gigantic mass in a tiny volume. It's the same story told by another narrator. When these centers are eating, the signature becomes even clearer. Falling gas doesn't collapse all at once. It spirals and forms an accretion disk, heats to millions of degrees, and shines from X-rays to ultraviolet. In this process, a surprisingly large fraction of mass becomes light. Black holes are very efficient engines. This is what feeds quasars, those cosmic lighthouses that shine brighter than entire galaxies. And this is what produces narrowed jets, threads of particles launched at near light speeds that traverse galaxies and inflate hot gas bubbles in clusters. There's no point looking for a solid surface. There's no floor for gas to hit. There's an event horizon, the no-return boundary predicted by Einstein. If the source is compact, luminous, and has no surface, the diagnosis fits. There's also a curious technique called reverberation mapping. Imagine the disk as a stage and surrounding gas clouds as an audience in layers. When the stage brightness varies, the audience responds with a delay that depends on distance. By measuring this delay, you measure the size of emitting regions and combining with line widths, which give gas velocity, weigh the central object. This scale, used in dozens of active galaxies, always points to masses of millions to billions of suns, concentrated where only a black hole would make sense. In recent years, two iconic signatures entered science pop culture and tied the final knot. The first were gravitational waves from pairs of black holes merging, the ringing of space-time itself when horizons join. Although first signals came from stellar mass black holes, they showed the final dance is real and measurable. The second was the shadow image. A global consortium of radio telescopes used interferometry technique to create an Earth-sized telescope and see the black hole at galaxy M87's center as a ring of light with a hole in the middle. Later, it repeated the feat with Sagittarius A*. The size and shape of these rings match relativistic prediction for event horizons of an object of that mass. It's not artistic illustration, it's data. If evidence is so strong, why wasn't this statement, "Most galaxies have a supermassive one at the center," obvious from the start? Because black holes are discrete when fasting. Most of the time, the center stays quiet, faint, mixed with light from surrounding stars. We easily see partying cases when there's lots of food on the plate, active nuclei. The work of the last 30 to 40 years was showing that even calm galaxies without bright nuclei hide a sleeping colossus. Orbital measurements, masers, reverberation, and in some cases, the shadow itself close the account. In practically all large galaxies with well-defined stellar bulges, there it is. This leads us to a natural question. What's the relationship between the central black hole and the galaxy that houses it? For a long time, they were thought to be independent characters. On one side, bulge stars, on the other, a point monster at the center. But when astronomers began comparing many galaxies, a strong correlation emerged. The more massive the stellar bulge, the more massive the black hole. There's also a link with the temperature of stellar motion in the bulge, how fast and chaotic they move. These relationships suggest co-evolution. As the galaxy grows, the black hole grows, and growing, it returns energy to the surroundings, heating, blowing, sometimes even breaking new star formation. This feedback appears in various forms. In galaxy clusters, for example, X-ray images reveal cavities in hot gas, as if something had inflated giant bubbles. Jets from the center, fed by the black hole, are obvious suspects. They deposit energy, push gas, prevent everything from cooling at once. On smaller scales, fast winds leaving the disk can sweep internal regions and prevent gas from condensing into stars. It's not that the black hole turns off a galaxy with a button, but it regulates the core's climate and influences star formation rhythm over billions of years. Another important piece is the distant past. When we look very far, we see the young universe, and to general surprise, we already find quasars shining less than 1 billion years after the Big Bang, which implies black holes with masses of hundreds of millions to billions of suns very early in cosmic history. How did they grow so fast? There are two paths discussed today. One is starting with light seeds, remnants of very massive stars with tens to a few hundred solar masses that then grow acceleratedly by swallowing gas and merging with other black holes. The other is starting with heavy seeds, direct collapses of giant gas clouds already born with 100,000 to 1 million solar masses. Maybe nature uses both at different times and environments. The point is that giant's presence in the baby universe forces us to think about efficient growth, with periods when the gas faucet was wide open. And how does gas reach the center? Partly through a galaxy's normal mess. Spiral arms, instabilities, stellar bars, all this can channel material inward gradually. Partly through encounters and mergers between galaxies. When two galaxies interact, gas feels tidal forces, loses angular momentum, and sinks. The center lights up. We see many merging galaxies with active nuclei and jets, sign of central banquet. And if each galaxy had its own black hole, these two, with time, form a pair and may end up merging, releasing very long-period gravitational waves. Experiments that timed pulsars like cosmic clocks already begin suggesting the presence of collective humming from these mergers throughout the universe. Let's talk a bit about the forbidden region itself without technicalities. A black hole's edge, the event horizon, isn't a solid surface. It's a causality limit. Cross it, no return. Outside, however, there's lots of physics. The disk seething, magnetic fields twisting, particles gaining energy. In fast-spinning black holes, the ergosphere emerges, an outer shell where nothing can stay still. Everything is dragged by space-time's own rotation. There, magnetic processes can steal a bit of the black hole's rotation and feed jets. When we look at the disk in X-rays, sometimes we see signatures of highly energized iron. This line's shape is distorted by gravity and extremely high velocities. It's an almost tabletop test of general relativity. In radio, hot spots in the inner disk seem to orbit in minutes in Sagittarius A star's case, drawing bright points that in the future we should follow in real time. It's also worth remembering that supermassive isn't synonymous with active. Most are quiet most of the time. Occasionally, a rare event breaks the fast. A star that comes too close is shredded by tides, a tidal disruption event. The resulting debris falls and illuminates the center for months. These outbursts are great because they light up, briefly, black holes that would normally be invisible. New surveys of brightness variation across the entire sky, those surveys that repeat sky photos night after night, have cataloged dozens of these flashes, helping weigh dormant black holes in ordinary galaxies. And in small galaxies, the rule of most with a supermassive at the center is clearer in galaxies with well-formed stellar bulges, ellipticals and spirals with bulges. In dwarfs and very light spirals, the picture is more diverse. Some have intermediate mass black holes, tens of thousands to hundreds of thousands of suns. Others might have nothing significant. This boundary is precisely where the seed story can be tested. If we find many intermediate black holes in dwarf galaxies, it favors certain formation pathways. If they're rare, it favors others. It's a living topic. All this holds up because we look at the same problem through different windows. In visible and infrared light, we measured the dance of stars and gas. In radio, we map jets, and now shadows. In X-rays, we see the seething disk and hot corona above it. With variability techniques, we measure sizes we can't directly resolve, and with gravitational waves, we hear mergers. The case's strength is convergence, different methods in different objects, pointing to the same character. What's ahead should make this story even more concrete. A space-based gravitational wave observatory, sensitive to periods from minutes to hours, should directly detect supermassive black hole mergers. It will be like listening to cosmic marriages in slow motion. Larger, more sensitive radio networks will refine shadow and jet images. New giant ground telescopes with adaptive optics will weigh black holes in more distant galaxies by following individual stellar movements. Surveys that repeat the entire sky night after night will catch more shredded stars and rapid variations in active nuclei, feeding statistics, and telescopes that see the baby universe will hunt the first quasars to understand how seeds were born and grew so quickly. At the beginning of the 20th century, people believed in the existence of only one galaxy, the Milky Way. At the beginning of the 20th century, the map of the universe fit on a single island, the Milky Way. The rest of the sky was a backdrop dotted with stars from our own galaxy, and, here and there, some diffuse patches called nebulae. Some were clearly gas clouds within the Milky Way. Others had spiral shapes seen on photographic plates, but many people thought they were whirlpools of matter in our cosmic backyard. The idea that there could exist other star islands the size of ours sounded extravagant. It was like looking at the ocean at night, seeing lights on the horizon, and swearing they're lighthouses from our own coast, never cities on other continents. At that time, telescopes were growing, astronomical photography was becoming routine, and spectroscopy, the study of light's rainbow, allowed knowing what stars are made of and whether an object was approaching or receding. But a reliable ruler for measuring large distances was still missing. Without knowing how far something is, everything becomes ambiguous. A nearby candle appears as bright as a very distant spotlight, so the spiral nebulae could be modest clouds nearby, or colossal structures far away. This impasse became famous as the Great Debate in 1920 between two American astronomers, Harlow Shapley and Heber Curtis. Shapley was the Milky Way's cartographer. Using globular clusters, those dense balls with hundreds of thousands of stars, he mapped these swarms' distribution and concluded that our galaxy center lay in Sagittarius direction, far from the Sun. Additionally, he estimated the Milky Way as immense, larger than previously thought. For him, spirals would be internal objects, perhaps star formation regions within our giant galactic system. Curtis, meanwhile, collected clues from the spirals themselves. Dust lanes, stars resolved at the edges, point explosions they called novae in Andromeda. Curtis's bet was different. Spirals would be island universes, independent galaxies far beyond the Milky Way. Historically speaking, it was a revelation. The universe suddenly grew. This result didn't fall from the sky in isolation. Since 1912, Vesto Slipher at Lowell had been measuring spirals' light tone and noticing many were reddened, that is, moving away from us. Years later, combining approximate distances and velocities, Hubble traced the now famous relation linking a galaxy's distance to the speed at which it recedes, the signature of universe expansion. But before expansion became news, the conceptual break had already occurred. The Milky Way wasn't the universe, it was one among many. Let's step back, because the story becomes richer when we look at the era's sincere doubts. In 1885, a flash appeared in Andromeda, dubbed S Andromedae. It seemed like a nova, a star that suddenly brightens, and many people used the calculation in reverse. If it were a typical nova within the Milky Way, Andromeda would have to be relatively nearby. Years later, we understood that flash was actually a much more energetic supernova. The misclassification pushed interpretations in the wrong direction for decades. Science is sometimes like this. One mislabeled piece distorts the entire puzzle, until another piece, in this case Leavitt's Cepheids, measured by Hubble, forces reorganization. Meanwhile, Shapley wasn't wrong about everything. On the contrary, he got something essential right. He removed the Sun from the Milky Way's center and showed our galaxy is wide and flattened, with the core much more distant than imagined. It was like moving the "you are here" pin to a map's edge. Curtis was right in defending external galaxies. In balance, both were seeing different parts of the truth. It's a good reminder of how knowledge advances, through approximations, with pieces that fit together gradually. After Andromeda came out of the closet as a galaxy, The rest came in cascade. Hubble and colleagues began classifying galaxies by appearance, ellipticals, spirals, barred spirals, not as something teleological, but as a way to organize data and look for patterns. With distance ruler improvements, Cepheids, supernovae, and other standard candles, they could build a scaffold of measurements, from stellar neighborhood to Magellanic Clouds, then to Andromeda, and subsequently to hundreds and thousands of galaxies. Suddenly, the sky stopped being a single disk with spots and became a web of archipelagos. This change wasn't just a scale adjustment, it changed questions. If there are many galaxies, how are they born and evolve? Why do some have spiral arms and others are diffuse ellipses? Why do many spirals have a bright bulge at the center, and what object lives there? Today we answer that most have supermassive black holes at the core, and they and galaxies grow together. But that's a story that only became possible after we accepted that galaxies exist as independent entities. The numbers also changed. By mid-20th century, photographic surveys were already counting hundreds of millions of galaxies. With the Hubble Space Telescope in the late 1990s came the deep field, pointing for days at a tiny piece of sky and seeing thousands of galaxies where almost nothing was visible before. Scaling this to the entire sky led to estimates of tens to hundreds of billions of galaxies in the observable universe, and this number could still grow with more sensitive instruments. All this stems from the initial step, recognizing that Andromeda wasn't our cloud. If you're thinking, how did nobody see this before? It's worth remembering early century technical limitations. Smaller telescopes, less sensitive photographic plates, dust from the Milky Way itself obscuring vision in certain directions, and absence of a firm ruler for extragalactic distances. Leavitt didn't discover Cepheids. She discovered the period luminosity relationship, the trick that transformed these stars into rulers. Hubble didn't discover Andromeda. He measured its Cepheids and showed it was very, very far away. Slipher didn't explain expansion. He measured radial velocities that later fit into a pattern. That's how a robust edifice is built, placing different bricks in the right place. There's also a beautiful human layer to this story. Henrietta Leavitt worked as one of Harvard's computers, women who measured and cataloged data in an era when official doors to scientific careers were closed to them. Her discovery is one of modern astronomy's pillars. Shapley, with his globular cluster measurements, had the courage to remove the sun from the center, a decision that always encounters cultural resistance. Curtis publicly debated an unpopular idea. Hubble had at his disposal the world's largest telescope and the ambition to use it for big questions. Nobody did everything alone. Everyone gave something the others needed. From a conceptual standpoint, the passage from only one galaxy to a universe of galaxies is related to other decentralizations in science history. Earth isn't the solar system center, the Sun isn't the Milky Way center, the Milky Way isn't the entire universe. Each stage displaces our symbolic place and expands the scenario, and each stage only solidifies when a measurement appears simple enough to resist doubts. In Galaxies' case, simplicity came with pulsating light that can be timed and compared, Leavitt's ruler, and with patience in following stars or gas rotating around invisible centers. And what remained from this turnaround for today's astronomy? Almost everything. The idea that each galaxy has its own history, intertwining with neighbors through encounters, mergers, and tides. The notion that there's a cosmic web, with galaxies aligned in filaments and voids, inherited from very ancient universe ripples. Understanding that there are active galaxies, where central black holes feed and blow jets, and passive galaxies, where star birth has cooled. And in our backyard, awareness that the Milky Way has a large neighbor, Andromeda, and that in a few billion years, the two will merge, forming a larger galaxy. All this makes sense because way back, we stopped treating spirals as internal clouds and began seeing them as distant cities. Voyager 1 is the most distant human-made object from Earth. Having crossed the heliosphere in 2012, Voyager 1 is, today, the most distant human-made object from Earth. Launched in 1977, it crossed the solar wind's domain, passed through the transition region where that wind loses strength, and in 2012 crossed the heliopause, the boundary where the sun's magnetic influence yields to the interstellar medium. From there onward, the spacecraft continues navigating in an environment different from what fills our solar system, a tenuous sea of particles and magnetic fields that circulates between stars. At this point, its distance already exceeds tens of billions of kilometers. The light it sends takes many hours to reach terrestrial antennas. It's a very large background silence, crossed by a weak but continuous data thread that carries the latest measurements from a mission that has already lived far beyond the time originally envisioned. The story began with a rare window of planetary alignment. When planning trajectories, engineers realized Jupiter and Saturn could serve as gravitational slingshots, saving fuel and increasing velocity. Voyager 1 departed with this objective, passed by Jupiter in 1979 and Saturn in 1980, collecting images, particle measurements, magnetic fields, and atmospheric data. It was a flyby, not a stop. The probe briefly dove into these worlds' vicinity and continued onward, always in free fall, always curving, always using gravity as leverage. At Jupiter, the craft gave us a shock of cosmic reality. The clouds and storms weren't just pretty patterns, they were living structures with lightning, turbulence, and vortices that changed within hours. The planet had tenuous rings, something almost invisible until then, and a magnetic environment so large it encompassed entire moons. At Io, Voyager 1 recorded something unprecedented: active volcanoes, eruptions happening there in real time, beyond Earth. At Europa and Ganymede, it saw scratched, fractured surfaces, clues to the idea of oceans beneath ice that would only gain strength later. Jupiter stopped being a distant ball and became a complete system packed with surprises. Saturn brought another set of revelations. The rings, which from afar appear as a single disk, emerged as a complex architecture cut by gaps and finest striations, subject to waves and ephemeral bridges influenced by shepherd moons. The atmosphere revealed bands and storms and subtle chemistry. The magnetic field danced in the instrument, and when pointing toward Titan, the largest moon, the camera found such a dense fog cover that nothing of the surface remained visible. That opacity said much. There was a robust atmosphere there, rich in nitrogen, capable of sustaining methane and ethane cycles. The passage by Titan was also decisive for the route. The encounter diverted Voyager 1 out of the orbital plane, ending the planet-visiting phase, but opening the path outward toward the solar space's edges. With the gas giant phase finished, began the long, patient, almost monastic phase of the mission. Without cameras on, they were turned off in the early 1990s to save energy. The probe began living mainly off its field and particle instruments. These are sensors that count ions, electrons, fine dust, that measure magnetic field direction and strength, that listen to plasma waves. All this builds a portrait of the invisible environment. Voyager 1 isn't fast on our daily scale, but by solar system standards, it advances well, kilometer by kilometer, astronomical unit after astronomical unit, moving away from the Sun in almost a straight line, pushed by the impulse gained in gravitational slingshots. To understand what it crossed, it's worth calmly describing the home it left. The Sun blows, constantly, a wind of charged particles. This flow pushes outward, inflates a magnetic bubble that envelops the planets, the heliosphere. At some very distant point, this wind encounters the interstellar medium. External pressure makes the solar wind decelerate in a shock, thicken in a crumpled layer, and finally practically stop at the boundary. The termination shock marks deceleration. The heliosheath, the region of weakened flow, is a turbulent corridor. The heliopause is the final door. It was this door that Voyager 1 crossed in 2012. On the other side, particle density is higher than in the heliosheath, magnetic field direction changes, and galactic cosmic rays, energetic particles from outside, begin arriving more freely. There's a beautiful detail in how we knew this. The instrument that would directly measure solar wind velocity on Voyager 1 had stopped working decades earlier. To infer the environment on the frontier's other side, the team needed to use different ears. The plasma wave detector is sensitive to electrical vibrations in rarefied gas. When a distant shock wave, born, for example, from a large solar mass ejection, reaches the craft's region, it makes the local plasma sing, producing a tone whose frequency depends on density. It was by listening to these whistles that scientists compared densities and concluded the craft was in a denser medium, typical of space between stars, no longer within the solar breeze. Throughout this crossing, particle counters told another story. Near the termination shock, the quantity of particles accelerated by the Sun rises. Afterward, this signal declines and the flow of galactic origin cosmic rays grows markedly. It's the outside signature. The magnetometer, meanwhile, records the invisible threads of field, direction, intensity, oscillations. Together, these data compose a silent logbook made of numbers the team translates into maps and profiles. There's no photography, but there's landscape. In the middle of this technical work exists a human chapter worth remembering. In 1990, at Carl Sagan's suggestion, Voyager 1 turned its camera for the last time and photographed Earth from about 6 billion kilometers away. The planet appeared as a pale point suspended in a light ray from the craft's own optical system. The image became known as the pale blue dot. It brought no new scientific data. It brought scale. It spoke of how small our home is within the vast darkness. After this gesture, cameras were turned off forever. The rest of the mission would be heard, not seen. As years passed, available energy diminished. The craft's electrical heart is a radioisotope thermoelectric generator. Heat produced by plutonium disintegration transforms into electricity. This heat decays slowly, year after year, and the team turned off systems to keep the most useful instruments alive. Heaters were cut, redundancies were disabled, backup channels were sacrificed. Even so, electricity still feeds sensors and radio. In some recent moments, data flow suffered from temporary computer failures. Still, engineers managed to recover telemetry and resume measurements. Everything is done with extreme care because each command takes many hours to go and return, and because there's no way to press a button if something goes wrong. Voyager 1's discoveries are therefore of two types. The first, in the inner solar system, revealed Jupiter and Saturn's complexity, their moons and rings, inaugurating a way of looking at giants that transformed questions into entire exploration programs. The most recent are less showy but equally fundamental. They defined for the first time in situ local interstellar medium properties, measured its electronic density, its magnetic field, its weather, affected by waves born many billions of kilometers away. Putting everything together, our map of the solar surroundings became clearer. We know where the sun's breath ends. We know what the rarefied air that begins afterward is like. There's also a cultural component carried by the craft. On the body's side, beyond instruments, goes a gold-plated disc, the Golden Record. There are recordings of greetings in dozens of languages, earth sounds, music, coded images, a kind of time capsule that isn't for us. It's not technology that helps the mission operate, it's a gesture. In tens of thousands of years, when the craft slowly passes near another star, maybe no one will see it, maybe no one will hear it. The disc is still a sincere message, a note left in a bottle. This is how we sounded. This is how we tried to say, hello. Communicating with Voyager 1 is a feat in itself. The onboard transmitter's power is comparable to an ordinary light bulb. The signal leaves the high-gain antenna, spreads through space, weakens, and upon reaching Earth, is collected by giant dishes of the Deep Space Network, 34 and 70-meter antennas distributed to cover the globe throughout the day. In some windows, to increase sensitivity, these antennas are combined as a single ear. Data rates are extremely low, measured in bits per second, but sufficient to transport the numbers that matter. It's like hearing a whisper from the end of the street on a windless night. Voyager 1's future is, paradoxically, simple. The craft will continue forward, following the same inertia, for thousands and thousands of years. Its electrical energy will diminish until no instrument can operate. The transmitter will one day fall silent. The metal body will proceed mute, crossing the galactic neighborhood like a grain of dust with history. It won't return to us, won't orbit another star, won't curve by its own will. It's a type of practical eternity, silent, slow, persistent. While sufficient electricity is available, however, each additional hour of operation is precious because it adds one more point to the density graph, one more field measurement, one more robust answer to the question, what exactly is it like out there? When we say it surpassed the heliosphere in 2012, we're saying that since then the craft offers something no other instrument has ever offered: direct measurements from the outside. This has discrete and profound implications. Models of how the sun's magnetic field interacts with the interstellar medium need to adjust to real numbers. The solar bubble's shape, its tail, its front, its asymmetries, everything gains concrete parameters. Pressure waves generated by major solar events take more than a year to cross the boundary and make sing the plasma where the craft is. The measured delay confirms distance and density. Space between stars stops being an abstraction and becomes a place with sound, even though this sound only exists for physics' ears. In parallel, the mission teaches a lesson about doing science with time. Nothing here is rushed. From launch to first Jupiter encounter, from Saturn crossing to pale blue dot photography, from termination shock crossing to heliopause announcement, these are chapters separated by years. Persistence bears fruit. An instrument not made to directly measure solar wind velocity finds another way to say what we need. An antenna not designed to hear such weak sounds learns with the right amplifier to listen. It's delicate carpentry work, done with the pieces that existed, that still exist, and with the patience of those who know space doesn't change its mind for our sake. Perhaps that's what's most relevant about Voyager 1 beyond all objective discoveries. The way it forces us to expand thought's rhythm, knowing there's a human artifact so far away operating at the possible's threshold, changes how we feel distance and time. Each bit's value magnifies, not for its content itself, but for the path it had to travel. What we learned about Jupiter and Saturn gave birth to new missions. What we learned about the heliosphere and interstellar medium prepares ground for next generations of probes. The craft is old, its electronics modest, but its function today is irreplaceable, a hand extended outward, gauging the wind that blows between stars. There are quasars so bright they exceed the luminosity of entire galaxies. There are lighthouses in the universe that shine brighter than entire cities of stars. We call these lighthouses quasars. In deep nights of cosmic history, when the universe was a few billion years old, they lit up with such force that they exceeded the luminosity of entire galaxies, sometimes 1,000, 10,000 times more light than the entire Milky Way produces today. And most surprisingly, this brightness doesn't come from a giant star or a single explosion, but from a disk of gas falling around a supermassive black hole. Its gravity converting fall into light with an efficiency that stellar nuclear fusion doesn't reach. To understand why a quasar can be so luminous, imagine two stages. First, the mill, a black hole at a galaxy's center with millions or billions of solar masses. Second, the fuel, gas and dust that, through gravity, spiral inward. This material doesn't fall straight down. It forms a disk, friction-heated. With each orbit, it loses some energy and falls to a more internal orbit, heating even more. Before crossing the point of no return, this gas reaches temperatures so high it shines from ultraviolet to X-rays. In practice, it's as if an important fraction of mass were transformed into radiation. While fusion in a star's heart converts less than 1% of mass into energy throughout its lifetime, falling into a rotating black hole can convert 10, 20, even something close to 40%. It's a very efficient engine, and that's why an object the size of the solar system can shine brighter than 100 billion stars together. The word quasar was born in the 1960s when radio telescopes began mapping very compact radio sources in the sky. In photographs, they looked like little stars, but their spectra, that barcode every light source carries, didn't match stars. One of them, in early 1963, revealed lines shifted to longer wavelengths. It was much farther than supposed, yet still shone like a local beacon. It was a reality shock. The universe had, after all, absurdly powerful lamps scattered across great distances. Gradually, it was discovered that not all quasars screamed on radio. Many were silent at that wavelength, but equally bright in optical and ultraviolet. The name stuck and understanding grew. Quasars are the most luminous face of the same phenomenon, active galactic nuclei, galaxy's heart when the central black hole is well fed. This heart has layers. At the center, the ultra-hot disk. Around it, gas clouds illuminated by the disk, moving at speeds of thousands of kilometers per second. That's why their emission lines appear broadened. It's the Doppler effect from clouds that come and go, a blur that betrays velocity and therefore the center's gravity. Farther out, a more diffuse region responds with narrower lines. And enveloping everything, a kind of dust corona heats and re-emits light in infrared. Depending on the angle we look from, we see more of the disk and broad lines, type 1 nuclei. Or we see the system from the edges, with dust hiding direct view of the disk and leaving only narrow lines to shine. It's not that different species of monsters exist. Often it's the same beast from different sides. If you want a simple test of how small the lighthouse is, look at the clock. Quasars vary in brightness. There are oscillations in days, weeks, months, and this alone says much. Nothing larger than the distance light travels in the variation period could alternate brightness so quickly overall. If a quasar blinks in a week, the region responsible for that light must be, at most, a few light days in size. That is, we're talking about a compact core, much smaller than an entire galaxy, producing more light than all of it. This compactness is the signature of accretion engines. In some special cases, one of the light threads emerges as a jet. Magnetic fields anchored in the disk and possibly in the black hole's own rotation, collimate particles to near light speeds and launch them outward at both poles. If one of these jets is pointed almost in our direction, the relativistic effect makes everything appear even brighter and more variable, what we call a blazar. These objects dominate gamma-ray and radio catalogs, reminding us that it's not just the disk that matters, the black hole's geometry and rotation add spectacle. But how bright exactly? Let's go with a friendly scale. The Milky Way emits something like tens of billions of sunlights combined. A typical quasar at its peak can emit 1,000, 10,000, sometimes more than that. Part of this difference comes from the engine efficiency, part from the fact that the black hole at the center, when fed, doesn't suffer the same yield limitation as a single star. There is, of course, a physical limit, the point where outgoing light pressure begins pushing away incoming gas. It's a balance. If it shines too much, it blows away the plate. If it shines too little, the whole plate falls in. Many quasars seem to operate near this natural limit, which functions as a cosmic volume control. The peak of quasars in the universe was a specific era, a few billion years after the Big Bang, the cosmological equivalent of adolescence. In that period, galaxies were forming and feeding intensely, mergers were common, and there was much available gas at the center. Not coincidentally, the brightest quasars we observe come from that era. Today, the universe is calmer. There are still active nuclei, but banquets are rarely like before. Even so, finding very distant quasars, from when the universe was less than a billion years old, gives us an interesting puzzle. How did a black hole reach billions of solar masses so quickly? Hypotheses vary. Maybe they were born from already large seeds, direct collapses of immense gas clouds. Maybe they went through very efficient feeding phases, maybe both. The most remote quasars we see are therefore clues about the first kitchens where galaxies and black holes began growing together. And this together deserves emphasis. The relationship between black hole mass and host galaxy stellar bulge properties suggests co-evolution. The center grows while the galaxy grows, and when the center lights up too much, it returns energy that can heat and expel gas, slowing new star birth. In X-ray images of galaxy clusters, we see cavities carved by jets acting as heaters. In optical spectra, we see winds of thousands of kilometers per second blowing outward. Quasars in this sense aren't just lighthouses, they're galactic climate regulators, preventing gas from cooling too quickly and turning into stars without control. How do we find quasars amid the galaxy crowd? Today, with large sky surveys, they appear by color signature, very blue in certain filters, or very red when light is stretched by distance, by mid-infrared brightness, hot dust betrays, by X-ray emission, by variability. Sometimes the universe's own gravity helps with the lens. A massive galaxy between us and a quasar can bend light and multiply the background image, creating 4 copies of the same quasar, or even an almost perfect ring. These lenses serve as double laboratories. They amplify the distant lighthouse and allow us to measure time delays between copies, a way to time the cosmos and even infer cosmic distances. The brightest quasars have an even broader effect. They illuminate the path. Their light crosses the rarefied gas of intergalactic space and, in doing so, picks up stamps. Hydrogen atoms along the way leave bites in the spectrum, in a pattern called the Lyman alpha forest. Each bite reveals the existence of a gas filament at a specific distance. Gathering many lines, we make a statistical map of the cosmic web. It's thanks to these lighthouses that we can study how gas between galaxies evolved, when it became ionized again after first stars ignited, how helium changed state in later epochs. Quasars are universe-probing instruments, not just interesting objects. Okay, but what exactly do we see in the spectrum that confirms the central engine? 3 clues suffice. First, very broad lines, only explained by clouds rotating at extremely high speeds near a deep gravity well. Second, a characteristic excess of ultraviolet light, the blue bump, typical of hot disks. Third, a signature of highly energized iron in X-rays, distorted by extreme velocity and gravity. We can extract from there how internal the emitting region is, almost as if we were measuring how many disk turns we see, adding variability which tells us size, and echo techniques when the disk brightness changes and gaseous lines respond with delay. We can even weigh the black hole without seeing it. Echo period, gas velocity, simple gravity calculation. There are also more veiled relatives, nuclei where dust and gas hide the disk from us in many directions. In these situations, the quasar exists, but its direct light is blocked. What arrives is the infrared echo and filtered narrow lines. That's why for years we underestimated how many quasars exist. Shrouded versions escaped simpler search methods. With instruments that see beyond optical, the hidden population began appearing. The picture we have today is more complete. There's a thick dust phase, possibly linked to mergers and stellar formation bursts, where the center is a bagged quasar. Later, winds and jets clear the path, and the nucleus becomes more exposed. At different times and angles, we see different versions of the same cycle. Not all absurd brightness comes only from the disk. Sometimes relativity itself gives a push to apparent luminosity. If part of the disk or a hot spot on it orbits at high fractions of light speed, light emitted in that direction gets slightly reinforced for those in line. It's the relativistic beaming effect. In jets, this reinforcement is even more dramatic. A blazar seems to pulse and shine more than it's worth, simply because it has headlights in our face. That's why in brightness statistics, the most extreme are almost always objects with jets pointed at us. One aspect that enchants many people is the temporal sensitivity we've already achieved. In Sagittarius A star, our galaxy's black hole, which is fasting and therefore weak, we've already seen hot spots completing orbits in minutes, very close to the limit where light can circle around. In distant quasars, which we can't resolve, we do the reverse. We measure echo delays between disk blinking and cloud blinking and infer where each region is. It's a map by time, not by space. With this, we trace scales. A more massive black hole blinks slower, like a whale's heart. A smaller one blinks faster, like a hummingbird's. These scaling laws reinforce the general picture. It's the same engine, in different sizes. And the question that won't die, why talk about quasars today if the current universe has few as bright as those from the past? Because they tie several stories into one. Without quasars, we'd lose a tool for measuring expansion in very ancient times. We'd lose the map of gas between galaxies. We'd understand less about black hole and galaxy coevolution, and we'd be without a natural laboratory of strong gravity, where general relativity is tested under extreme conditions. Moreover, new generations of telescopes in space and on ground are discovering increasingly distant quasars and detailing their surroundings with previously unthinkable clarity. A quasar that today is a point may tomorrow become a ring with irregularities, a shadow at the core, a jet with moving blobs. The universe may end in a big freeze, big rip, or gravitational collapse, scenarios still under debate. When we talk about the universe's end, we're not choosing a movie ending. We're reading a cosmic contract whose main text we already understand, but whose fine print we're still deciphering. We know the universe is expanding and that this expansion is currently accelerating. We know stars are born and die, galaxies drift apart, and light, as it travels, becomes increasingly stretched and cold. What we still don't know is how this motion ends. Among the most discussed scenarios are three quite different pictures: the big freeze, the big rip, and gravitational collapse, sometimes called the big crunch. Each is a logical continuation of what we've already measured. Just change one parameter here, one behavior there, and the final destiny changes tone. The key to everything, as we'll see, is the nature of dark energy, that mysterious push that accelerates expansion today. Let's start with what isn't in dispute. The universe has been expanding since the Big Bang. This means that, on large scales, distances increase with time. We discovered in the late 1990s that this expansion isn't just continuous, it accelerates. Something permeates space and, instead of pulling, pushes, at least in effective behavior. Call it vacuum energy, cosmological constant, dark energy. The question isn't the name, it's how does it behave? If this push is the type that remains stable and smooth, one future. If it's more aggressive and grows with time, another. If it weakens and allows gravity to regain control, yet another. That's why the three endings below sound plausible and why they're still debated. Each corresponds to a different personality of dark energy, and our current rulers haven't yet pinned down which is the true one. In the Big Freeze scenario, also called heat death, expansion continues forever and the universe becomes increasingly cold and sparse. Think of a campfire in an open field. While there's wood, there's light and heat. Gradually, the sticks run out, the embers become spaced apart, and heat spreads into increasingly cold air. On cosmic scale, wood is interstellar gas capable of forming stars. Today, galaxies still have enough gas for new cycles, but the star birth rate was more intense in the distant past. Over time, gas stocks are exhausted. Short-lived stars explode and vanish. Long-lived ones gradually wither. In trillions of years, the last red dwarfs, small economical stars, finish their fuel. Without replenishment, night has no new fires to light. This death isn't a sudden extinguishing, it's an elongation of night. Even after stellar formation ends, remnants remain. White dwarfs cooling for absurd ages, neutron stars, black holes, frozen planets wandering. The universe's ordinary matter becomes an inventory of remains. If protons are absolutely stable, particle physics hasn't yet delivered the verdict. These remnants persist indefinitely, only cooling and drifting apart. If protons decay very slowly, the scenario becomes even more crumbly. Over incomprehensible times, ordinary matter itself dissolves into radiation. And black holes? They dominate the final phase, swallowing whatever they find nearby, but also lose mass, very slowly, through a quantum effect. A black hole comparable to the supermassive ones at galaxy centers would take such an enormous time to evaporate that it needs almost poetic comparison. A number of years with 100 zeros or more. When even they disappear, what remains is a sparse ocean of photons and light particles, cold, homogeneous, without contrasts. A universe without clocks, because nothing meaningful changes. It's the silent ending. Nothing breaks, nothing tears, it simply fades from lack of fuel and excess space between things. Now, change dark energy's personality and the ending changes genre. If the push that accelerates expansion is not just constant, but grows with time in a specific way, stronger than a simple vacuum push, we enter Big Rip territory, the Great Tear. Here, it's not just that galaxies move apart faster and faster, it's that the separation rate accelerates so rapidly that systems' very cohesion is threatened. First, galaxies lose connection with the rest of the universe. This already happens in a certain way, but in the Big Rip, the story accelerates. Then, the force that held galaxies together gives way. Stars stop orbiting the center. Everything is torn away by expansion. Next, stellar systems, like ours, cease being stable. Planets separate from stars before these even finish their natural lives. If we follow this sequence to the limit, in a final time interval that could be billions or trillions of years from now, depending on how aggressive dark energy is, even atoms are torn apart. Because accelerated expansion, viewed locally, acts like a field that overcomes binding forces. It's a dramatic ending. There isn't a lack of energy. There's too much energy of the wrong type, and it breaks everything gravity and internal forces try to keep together. This dismantling's chronology is almost cinematic. Long periods with nothing special, final centuries with galaxies falling apart, perhaps millions of years later, planetary systems coming loose, final minutes or seconds with molecules and atoms losing cohesion. There's finally the possibility that the universe, instead of dying from cold or excessive separation, reverses course and collapses, the big crunch. For this, two things could happen. The first is geometric and accounting. If the universe's average density were high enough and there were no persistent push, gravity would break expansion to a stopping point and then pull everything back. It's like throwing a stone upward. If initial energy isn't sufficient, it rises, loses steam, and falls. The second is more sophisticated. Even if the push exists today, it might change character in the future, weakening, changing sign, or turning off after a certain time. If this happened, gravity would have a chance to regain control. In either case, the movie runs in reverse in certain passages. Galaxies that today separate would begin converging. The sky's background, which today cools, would heat again. Matter would condense. The rhythm of encounters and mergers would increase, and at some point, all visible content would be in an increasingly smaller, increasingly hotter space. Unlike the Big Freeze, here you return to having a luminous soup of radiation, and structures dissolve because everything gets too hot. Some models try to give this fall a shock absorber, a bounce, a rebound, where extreme collapse converts into new expansion. It's tempting to imagine a cyclic universe, but the physics of this shock absorber requires ingredients we don't yet master. What matters is that collapse is a plausible ending if the current push loses strength or disappears. Which of these scripts is most likely today? The weight of current observational evidence points to dark energy behavior very similar to a vacuum constant, that is, a smooth and stable push. If that's really it, the Big Freeze is the shelf ending. No tears and no return, just infinite expansion and general cooling. But similar isn't identical, and measurements have error bars. Small differences in behavior over time, almost imperceptible today, decide the plot in trillions of years. That's why there's so much effort to measure more precisely how expansion varied in the past, using distant supernovas as standard candles, mapping fossil ripples in galaxy distribution, and observing the oldest radiation we can see. Each method is a lens for seeing whether this push has always been equal to itself or changes subtly with time. In each ending there are variations worth noting. In the Big Freeze, artistry lies in intermediate acts. After star formation ceases, there's a long period when remaining light comes from old stars and hot remnants. Over time, this light migrates to increasingly longer wavelengths, invisible to human eyes, until it becomes cold noise. On tremendous timescales, rare encounters between dark objects, black dwarfs, neutron stars, can still happen, generating late sparks. The big particle physics question, do protons decay or not, decides whether ordinary matter persists forever, or if someday only radiation and possible remnants of a particle sector we don't even know exist remain. The Big Freeze's beauty, so to speak, is that it doesn't depend on a spectacular mechanism. It depends only on persistence of what we already see, accelerated expansion and finite gas stocks for new stars. In the Big Rip, a technical detail governs the sequence, but it can be explained without jargon. It's as if the pressure associated with dark energy were so negative that when you put the universe in equations, the term that accelerates expansion grows with the growth itself. It's a snowball effect. The bigger it gets, the faster it becomes, and the faster it becomes, the bigger it gets. The universe doesn't just expand, it expands the capacity to expand. When this happens, no scale is safe. First fall loose ties between galaxies, then internal bonds of each galaxy, next gravities of stars and planets, Finally, matter's internal bonds. That's why the final moments would be so dramatic, a general dismantling that affects everything from supercluster to atom. In gravitational collapse, what's interesting is that time's arrow is maintained, but milestones return to resemble those of the cosmos' infancy. A sea of radiation, energetic particles, extreme densities. The difference is that the path there is full of deconstructions, galaxies that merge, black holes that grow by devouring everything nearby, entire regions that heat with compression. It's a hot, noisy, luminous ending, the opposite of big freeze silence. If a bounce is possible, the next story is born from maximum heat. If not, it ends there, in a singularity where our theories stop speaking. What if none of these is the right ending? It's an honest question. Other drafts exist on the table. There's, for example, the possibility that the vacuum we know isn't the most stable state, and that, after gigantic time, a bubble of a more energetic or more stable state forms and expands at light speed, changing physics rules locally, something like a big slurp. It's a particle physics scenario, not large-scale gravity, and depends on parameters we're still measuring with growing precision. There are also versions of cyclic universes where bounces are part of a larger mechanism, with losses and gains each cycle. They're interesting because they escape endings where everything ends. Instead, everything restarts with variations. For now, however, the freeze-rip-crunch trio covers most of the possibility space connected to what we've already measured of expansion. Why is talking about such distant endings worthwhile today? Because what determines the distant tomorrow is the same thing that subtly governs today. Better measuring dark energy, understanding if its strength changes with time and how space responds to it. All this affects not just the last chapter, but intermediate chapters, structure formation, galaxy growth rhythm, star birth history, current and future missions, those mapping millions of galaxies, precisely measuring stellar explosion brightness, listening to gravitational waves from black hole pairs, and someday perhaps even from supermassive pairs, serve to tighten the screws on this prediction. Cosmology in this sense is a workshop. Each new tool tightens one point, and when all points are firm, the furniture doesn't wobble, and the ending stops being one of three to become, it's this one here. Perhaps the most comforting aspect, if we can speak that way, is realizing that none of these endings reaches us on human scales. We're talking about billions, trillions of years, numbers that don't fit on a notebook line. This doesn't diminish the problem's grandeur. On the contrary, it increases our freedom to pursue it without urgency. The TRAPPIST-1 system harbors 7 rocky planets, some in the habitable zone. 40 light-years from here, in a patch of sky called Aquarius, exists a cold, small star, much smaller than the Sun. Around it, packed tight like beads on a necklace, orbit 7 Earth-sized worlds. They form the TRAPPIST-1 system, and it's hard to overstate how much it changed our search for other habitable places. When astronomers announced the discovery in 2017, they weren't talking about one interesting planet, but an entire family with several siblings receiving amounts of light similar to what Earth receives. Some, in fact, in the so-called habitable zone, where liquid water could exist on the surface. It was a milestone, the kind that makes it into science history summaries. The star itself is quite modest, an ultra-cool red dwarf with about 9% of the Sun's mass and size close to planet Jupiter's, though it's a real star, fusing hydrogen in its core. It's old. The best estimates point to around 7.6 billion years, older than our solar system. This age detail matters. It gives worlds time to change, lose or gain atmospheres, accumulate ice, and perhaps stabilize climates. But it also means long exposure to particle bursts and energetic light, typical of red dwarfs. How did we arrive at such an intimate portrait of such a distant system? First, someone noticed tiny blackouts in the star's light, brightness drops that repeated like clockwork, These are transits. When a planet passes in front of the star, it blocks a bit of light, betraying its presence. From these transit patterns, astronomers counted how many worlds there were and measured their sizes. Intensive campaigns on the ground and with the Spitzer Space Telescope revealed Swiss watch architecture, 7 orbits, all very close, with periods from 1.5 to 18.8 days. In an even subtler dance, planets gravitationally pull each other and arrive slightly early or late to transits. It's from this back and forth that we extract masses and densities, discovering they're truly rocky. This dance is so organized it forms a resonance chain, as if each planet kept time for the next, a sign they migrated close to the star in the past and were fitting synchrony along the way. Proximity to the star brings another consequence. Almost all should be tidally locked, always showing the same face to the star, like the moon does with Earth. This sounds extreme. One side in eternal day, the other in perpetual night. But nature is rarely black and white. If a reasonably pressurized atmosphere exists, it can transport heat from dayside to nightside and soften extremes, perhaps allowing a mild band, that permanent twilight along the terminator, the line separating day from night. Atmospheric circulation studies suggest that with something on the order of tenths to 1 bar of pressure, this transport becomes efficient. From pressures of about 1 bar, the planet's thermal signature begins departing from that of bare rock. This is one of the ideas animating the community. Locked worlds don't need to be worlds frozen on one side and scorched on the other. Of course, habitable zone isn't a promise, it's a possible scenario. In TRAPPIST-1, it mainly involves planets E, F, and G. They receive on average light fluxes that could sustain liquid water on the surface, depending on atmosphere, clouds, ice, soil composition, and many ifs. The original announcement already highlighted this. It wasn't just the number of planets, but the fact that several fall in an interesting region for chemistry and climate. Since then, the system has become the standard laboratory for testing our techniques for sniffing out atmospheres on small worlds. The next step was asking, is there air there? Before James Webb, Hubble and Spitzer had already given an initial sweep. They didn't see the typical fingerprint signals of primordial atmospheres made of light, puffy hydrogen on the inner planets, a type of envelope that, if it existed, would produce strong marks in spectra during transits. In direct language, if there were inflated hydrogen coats on these worlds, we would have noticed. We didn't. This narrowed possibilities. Either there's no atmosphere of this type, or it's much denser and heavier, CO2, N2, water vapor, and therefore harder to notice with those instruments. The James Webb Space Telescope's arrival changed the game. With sensitivity and reach in mid-infrared, it can measure thermal brightness from planets' daysides when they pass behind the star, the so-called secondary eclipse. That's how, in 2023, Webb measured the illuminated face of TRAPPIST-1b, something around 500 kelvins, near 230 degrees C. This matches much better with a bare rocky surface without atmosphere redistributing heat than with a world covered by a gas mantle. In summary, B, the innermost, is probably a scalding rock without significant air. That same year, another Webb analysis looked at TRAPPIST-1c, the second planet. The target there was a specific CO2 signature at 15 micrometers wavelength. If there were a thick, CO2-dominated atmosphere like Venus's, the planet would appear darker precisely at that color. That's not what happened. The result shows that a bulky CO2 mantle is unlikely in C. Data are more compatible with a rocky surface planet without air or with a very thin gaseous envelope, perhaps dominated by residual oxygen with little CO2. None of this kills chances for the more external siblings, but indicates the family doesn't have, at least in worlds closer to the star, those fluffy, inflated atmospheres that would be easier to detect. And the darlings E, F, and G? We're still accumulating observations. Models show that even modest atmospheres can survive if the loss rate to space isn't too high. But red dwarfs, especially early in life, can be devilish. They release ultraviolet radiation and particle bursts that sand planets' upper air layers. In TRAPPIST-1's case, there are two partial good news items. The star is old, suggesting calmer activity today, and recent measurements suggest flare-effective temperatures may be lower than we thought, which somewhat changes damage calculations. Still, it's a demanding environment. The balance between sculpting and preserving atmospheres is one of the central dramas in this story. The TRAPPIST-1 system harbors 7 rocky planets, some in the habitable zone. 40 light-years from here, in a patch of sky called Aquarius, exists a cold small star, much smaller than the Sun. Around it, packed tight like beads on a necklace, orbit 7 Earth-sized worlds. They form the TRAPPIST-1 system, and it's hard to overstate how much it changed our search for other habitable places. When astronomers announced the discovery in 2017, they weren't talking about one interesting planet, but an entire family, with several siblings receiving amounts of light similar to what Earth receives. Some, in fact, in the so-called habitable zone, where liquid water could exist on the surface. It was a milestone, the kind that makes it into science history summaries. The star itself is quite modest, an ultra-cool red dwarf with about 9% of the Sun's mass and size, close to planet Jupiter's. Though it's a real star, fusing hydrogen in its core. It's old. The best estimates point to around 7.6 billion years, older than our solar system. This age detail matters. It gives worlds time to change, lose or gain atmospheres, accumulate ice, and perhaps stabilize climates. But it also means long exposure to particle bursts and energetic light, typical of red dwarfs. How did we arrive at such an intimate portrait of such a distant system? First, someone noticed tiny blackouts in the star's light, brightness drops that repeated like clockwork. These are transits. When a planet passes in front of the star, it blocks a bit of light, betraying its presence. From these transit patterns, astronomers counted how many worlds there were and measured their sizes. Intensive campaigns on the ground and with the Spitzer Space Telescope revealed Swiss watch architecture. 7 orbits, all very close, with periods from 1.5 to 18.8 days. In an even subtler dance, planets gravitationally pull each other and arrive slightly early or late to transits. It's from this back and forth that we extract masses and densities, discovering they're truly rocky. This dance is so organized, it forms a resonance chain, as if each planet kept time for the next, a sign they migrated close to the star in the past and were fitting synchrony along the way. Proximity to the star brings another consequence. Almost all should be tidally locked, always showing the same face to the star, like the moon does with Earth. This sounds extreme, one side in eternal day, the other in perpetual night. But nature is rarely black and white. If a reasonably pressurized atmosphere exists, it can transport heat from dayside to nightside and soften extremes, perhaps allowing a mild band, that permanent twilight along the terminator, the line separating day from night. Atmospheric circulation studies suggest that with something on the order of tenths to 1 bar of pressure, this transport becomes efficient. From pressures of about 1 bar, the planet's thermal signature begins departing from that of bare rock. This is one of the ideas animating the community. Locked worlds don't need to be worlds frozen on one side and scorched on the other. Of course, habitable zone isn't a promise, it's a possible scenario. In TRAPPIST-1, it mainly involves planets E, F, and G. They receive, on average, light fluxes that could sustain liquid water on the surface, depending on atmosphere, clouds, ice, soil composition, and many ifs. The original announcement already highlighted this. It wasn't just the number of planets, but the fact that several fall in an interesting region for chemistry and climate. Since then, the system has become the standard laboratory for testing our techniques for sniffing out atmospheres on small worlds. The next step was asking, is there air there? Before James Webb, Hubble and Spitzer had already given an initial sweep. They didn't see the typical fingerprint signals of primordial atmospheres made of light, puffy hydrogen on the inner planets, a type of envelope that, if it existed, would produce strong marks in spectra during transits. In direct language, if there were inflated hydrogen coats on these worlds, we would have noticed. We didn't. This narrowed possibilities. Either there's no atmosphere of this type, or it's much denser and heavier, CO2, N2, water vapor, and therefore harder to notice with those instruments. The James Webb Space Telescope's arrival changed the game. With sensitivity and reach in mid-infrared, it can measure thermal brightness from planets' day sides when they pass behind the star, the so-called secondary eclipse. That's how, in 2023, Webb measured the illuminated face temperature of TRAPPIST-1b, something around 500 kelvins, near 230 degrees Celsius. This matches much better with a bare, rocky surface without atmosphere redistributing heat than with a world covered by a gas mantle. In summary, B, the innermost, is probably a scalding rock without significant air. That same year, another Webb analysis looked at TRAPPIST-1c, the second planet. The target there was a specific CO2 signature at 15 micrometers wavelength. If there were a thick, CO2-dominated atmosphere like Venus, the planet would appear darker precisely at that color. That's not what happened. The result shows that a bulky CO2 mantle is unlikely in C. Data are more compatible with a rocky surface planet without air, or with a very thin gaseous envelope, perhaps dominated by residual oxygen with little CO2. None of this kills chances for the more external siblings, but indicates the family doesn't have, at least in worlds closer to the star, those fluffy inflated atmospheres that would be easier to detect. And the darlings, E, F, G, we're still accumulating observations. Models show that even modest atmospheres can survive if the loss rate to space isn't too high. But red dwarfs, especially early in life, can be devilish. They release ultraviolet radiation and particle bursts that sand planets' upper air layers. In TRAPPIST-1's case, there are two partial good news items. The star is old, suggesting calmer activity today, and recent measurements suggest flare-effective temperatures may be lower than we thought, which somewhat changes damage calculations. Still, it's a demanding environment. The balance between sculpting and preserving atmospheres is one of the central dramas in this story. Another puzzle piece is these worlds' own recipe. The best mass and radius measurements point to Earth-like densities, but with a detail. They seem, on average, slightly less iron-rich. This could mean somewhat smaller cores and mantles with more oxygen, which fits the idea that these planets formed far away where ice was more common, then migrated close to the star, losing some volatiles along the way. It's well-founded speculation, and each new Webb constraint helps fine-tune this origin story. While the portrait gains clarity, it's worth remembering how we measure these things. Sometimes we see the planet's shadow, transit, and adding many events, get a transmission spectrum, starlight filtered by the planet's atmospheric edge, if it exists. Other times we look when the planet hides behind the star, secondary eclipse, and measure thermal brightness that turns off and turns on, estimating day-side temperature. In worlds without atmosphere, day tends to be very hot and heat doesn't flow to night. In worlds with sufficient air, day-night difference decreases. This climate reading at distance through small light dives is poetry of engineering and statistics. And possible climates. In locked worlds, circulation tends to form winds that carry heated air from the subsolar point, directly under the star, toward the dark side, where it cools and sinks. Depending on pressure and composition, this can sustain clouds at the day-night edge, even generating a habitable band at the terminator. Not the entire planet comfortable, but a ring where conditions resemble eternal late afternoon. This concept of partial habitability has gained strength in recent years. It's less photogenic than an integral blue globe, but may be more realistic for worlds so close to red dwarfs. There's also the spice of tides. In TRAPPIST-1, planets are so close to each other that it's not just the star pulling and deforming. Neighbors themselves can raise tides, heat interiors, and in some cases maintain volcanism and gas recycling. It's a double-edged sword. Internal heat can feed atmospheres and maintain magnetic fields. Too much heat can cook and sterilize. TRAPPIST-1's charm is precisely this. It's a laboratory where all these forces, radiation, tides, migration, atmospheric loss, are acting extremely and measurably. If you're wondering, so is there an Earth twin there? The honest answer for now is, we don't know. What we do know is valuable. The two innermost planets, B and C, don't exhibit signs of thick atmospheres. Specifically, B seems like hot rock without air, and C doesn't have a CO2 coat like Venus's. For E, F, and G, the most cherished bets, the game is open and instruments are pointed. Each new transit added improves sensitivity. And it's not just Webb. Giant telescopes under construction in Chile should gather more clues from the ground, while other space missions throughout this decade should refine our ability to see thin gases, clouds, and even signs of magnetic field interaction. Curiously, TRAPPIST-1 taught us something about expectations. When the discovery came out, many dreamed of 7 Earths waiting for us. Today, what we have is more interesting. A reminder that Earth-sized worlds are diverse. They can be dry with oxidized crusts. They can have little air. They can host hidden old ice. They can have climates dominated by twilight ring clouds. And somewhere in this range there may be a good combination, not an Earth copy, but a distant cousin that solves climate differently and still allows liquid water here and there. This prudence doesn't diminish hope. On the contrary, it frees us from romantic filters and delivers better questions. What do we really need to measure to say there's stable climate? How much water is necessary? Global oceans, or do terminator ponds suffice? How do we distinguish between oxygen produced by life and oxygen left as leftovers after starlight separates water and hydrogen is lost to space? And methane, in such an environment, would it be biological or geological signature? These questions are the heart of honest astrobiology, which prefers slow, solid answers to rushed announcements. There's almost a philosophical detail in this story. TRAPPIST-1 is small, cold, and modest, the type of star most common in the galaxy. If a handful of these systems harbor several rocky planets, some with marginally stable climates, then the cosmos's rule isn't our sun. It's the modest multiplication of red stars with worlds glued to them, very close to the fire, but perhaps protected by gas veils, by stubborn clouds, by tides that feed the interior. It's not that Earth is rare, it's that diversity is the norm. All this to say, the TRAPPIST-1 system is less an answer and more a mirror. In it, we see our methods maturing, from seeing shadows to feeling heat, and we let enthusiasm coexist with patience. We also see a warning. Life, if it exists there, will have to negotiate an active sky, a star that was fierce early on, a peculiar climate. But life, in our local experience, likes to negotiate. When the next analyses come out, more transits added, more secondary eclipses, perhaps the first hint of a humble atmosphere in E, F, or G, the conversation will change tone a bit again. Maybe we'll find a thin CO2 shell here, a trace of water there, a cloud and dew cycle that balances dayside heat. Maybe we'll find only hot and cold rocks, and even then we'll learn about how rocky worlds lose and gain air. In any case, TRAPPIST-1 will continue being worth its weight in gold, a set of 7 natural experiments, all on the same bench, patiently waiting for us to learn to read what light tells us. The observable universe contains at least 100 billion galaxies, but new estimates suggest this number could be double. Imagine looking up and seeing an archipelago of lights floating in a dark ocean. Each point in the sky isn't a solitary lamp, but an entire city of stars, dust, and gas. When we say the observable universe contains at least 100 billion galaxies, we're trying to put a number on something that resists being counted. And when new estimates suggest this number could be double, it's not an exaggeration. It's the reflection of a vision that becomes clearer as we stretch our cosmic exposure. It's like turning off the last lights in the room to finally see the faint glow that was always there. How do you count the uncountable? The answer is less grand than it seems. We take a photograph of a tiny piece of sky, a frame so small it would fit behind a grain of sand on your fingertip, with telescopes pointed for long hours, sometimes days. In this almost empty frame, diffuse spots begin to appear, small blurs that, with patience, reveal spirals, ellipses, clusters. We count these blurs, measure their distance, estimate their luminosity, and then extrapolate to the rest of the sky. It's not a guess, it's sampling. It's not perfect, it's the best we can do when the showcase is so deep that light must cross ages to reach us. But why does the number change? Because the universe isn't just distant, it's shy. Very ancient galaxies are small, discrete, emitting light pushed toward tones invisible to our eyes. Others are hidden by dust, by nearby stellar brightness, by the instrument's own limits. Sometimes they're there, but the sky background swallows them, like weak candles on a foggy night. When we change eyes, when we observe an infrared, when we leave the camera open longer, when we combine light from many nights, the candles reappear, and what seemed like emptiness becomes a silent marketplace full of signals. There's a useful image to bring both sleep and clarity. Think of the cosmos as a beach and galaxies as half-buried shells. The largest, bright ones catch the eye. The smaller ones, covered by fine sand, remain invisible until we slowly run our hand over them. Telescopes like Hubble taught us to see the larger shells. More recent instruments capable of seeing wavelengths that penetrate dust and distance run their hand more delicately and find shells that previously escaped. As this gesture repeats, night after night, observatory after observatory, the count rises. Not because the universe suddenly manufactured new galaxies, but because our flashlight got better. Counting galaxies is counting in time, not just space. Looking far is looking back. The galaxies we see at the edges of our observable sphere are young versions, hurried, still assembling. Some appear more numerous than we imagined. Many are less luminous than we can easily detect. And what we see today isn't a single photograph. It's a mosaic of eras. In certain distance ranges, the number of small galaxies grows. In others, galaxies merge and become one. Statistics change. The landscape becomes more adult. All this enters the count. All this pushes the needle between at least 100 billion and could be double. There are also natural lenses scattered across the sky. Immense masses bend light from even more distant galaxies, as if space itself were thick glass. These gravitational lenses magnify faint objects, stretch their light, bring details we'd never see without them. When we adjust the right magnifying glass, more galaxies appear. When the magnifying glass isn't in place, they pass silently, like boats without beacons. Statistics must consider both cases, with and without magnifying glass, to neither overestimate nor miss. It's a patient game of corrections and care that transforms blurs into numbers. Another reason for the number dance is that the universe isn't homogeneous like creamy soup. It's more like a web. There are regions with dense filaments, where galaxies sprout like fruit in clusters, and there are enormous voids, where lights are rare and distant. If your sample falls on a filament, you count many. If it falls in a void, you count few. That's why we need many sky windows opened in different directions, and we need to add night after night until highs and lows dissolve into a reliable average. What we call at least 100 billion is this average, arranged with the care of those who don't want to promise too much, but also don't want to hide what night reveals. Deep down, the question, how many galaxies exist, brings another. What do we call the observable universe? It's not a box with fixed walls. It's a bubble that depends on light that's had time to reach us. Beyond this bubble, it's not that there's nothing more. It's that we don't yet have a way to know. Within it, space is expanding, and this stretches light waves, cools signals, transforms what's visible today into a harbinger of what will someday cease to be. That's why the number we give now isn't definitive. It's a family photograph taken at a specific moment with the camera we have. Why does it matter to know if it's 100 billion, 200 billion, or a bit more? Because each galaxy is a laboratory, a collection of stories. More galaxies mean more different environments for stars to form, more types of chemistry happening, more variations of dust, magnetic fields, and explosions. It means more variations of cosmic cities, some tranquil, others noisy, some spiral-shaped, others patched by ancient mergers. It also means more opportunities for worlds, for atmospheres, for the unexpected. The number alone doesn't tell us who lives where or how, but it gives an idea of how vast the stage is. When you hear double, don't imagine a sudden leap, a last-minute announcement. Instead, imagine a dark room where gradually your eyes adjust. First you see the larger shapes, then tiny contours begin appearing, shadows within shadows. What changes is sensitivity, patience, persistence. The cosmos isn't in a hurry, it permits. And when we allow ourselves to observe it long enough, we discover that the fabric that seemed smooth is actually embroidered. There's technical delicacy hidden in this calm. The sky background isn't ink black. It has its own glow, caused by everything shining at once. Very diffuse galaxies get lost in this backdrop. Correcting this backdrop, separating what's noise from what's signal, is craftsman's work. In parallel, we need to differentiate what's a distant galaxy from what's a star in our backyard or a dust speck caught along the way. This refinement helps avoid double counting, avoid losing what's weak, avoid including what shouldn't be on the list. It's careful, it's silent, and it's what, in the end, adjusts the ruler. Look again at the grain of sand analogy. A tiny rectangle of sky revealed thousands of galaxies when observed with obsessive attention. Now mentally multiply this rectangle across the entire firmament. You don't need exact numbers to feel the scale. Just imagine that each little piece of the heights hides a swarm of light islands. That's how at least 100 billion stops being just a phrase and becomes a physical sensation, a gentle weight in the chest. The world is larger than would fit in a single dawn. It's also good to remember that galaxy is a common name for very different things. Some are large and majestic, with arms that open like whirlpools. Others are almost diffuse spheres without apparent design. There are active ones with black holes at the center feeding powerful jets. There are those that seem asleep, with few new stars. When we improve our sight, what grows isn't just the count, it's variety. And variety is the raw material of understanding. It's what allows us to compare, group, tell stories that make sense. On the near horizon, new sky maps are combining depth and breadth, not just digging deep into small frames, but covering enormous areas with enough sensitivity to recognize the faint and distant. It's as if after learning to appreciate a miniature, we open the whole house's windows. The result is a fairer catalog of what exists, less subject to the whims of a single direction, more faithful to the cosmic web's design. All this happens while time runs, and it's curious how this race doesn't rush us. Contemplating such numbers invites slowing down. Instead of memorizing statistics, we can keep images, the sky as a silent forest, where each galaxy is a tree with its own age, its own trunk, its own cycle. In some places the forest is dense, in others it opens into a clearing. Our place, the Milky Way, is a tree among trees. And what the deepest surveys are saying is there are more trees than we supposed, and there are trees so thin and fragile they only appear when we let our eyes rest for a very long time. There's a gentle, almost poetic detail. When new estimates say could be double, they don't demand you believe without thinking. They invite you to imagine how invisible is what's very small and very far. They invite accepting the map changes because the flashlight changes. They invite embracing the idea that reality is always a bit richer than the moment's inventory. It's not a trick, it's method maturity. And what does this say about us? It says we're part of a calm exercise, reducing uncertainty drop by drop, looking again, redoing the count, comparing our sky rectangle with the neighbor's, joining the two images, letting dust settle. It says haste hinders, patience rewards. It's a simple lesson, but profound. The universe offers itself to those who remain. If tomorrow someone comes with a slightly larger number or slightly smaller, it won't be a contradiction, it'll be another layer of attention. Maybe we'll better recognize galaxies so diffuse they seem like clouds. Maybe we'll filter more rigorously a type of noise that confused the count. Maybe we'll discover that in certain ancient times there were more small systems than we supposed, and many merged over eras, like streams becoming rivers. What matters isn't the final answer, it's the gesture of approximation. At day's end, going to sleep with this image in the chest is easy. The sky is a tapestry of islands, and each year we embroider a few more hidden stitches. We don't need to memorize the total, just remember it grows with our ability to hear the faint. At least 100 billion is a humble way of saying we've already seen much. Could be double is a generous way of admitting there's still much to see. So, if you want to keep a simple phrase, keep this one. The universe is more populous than it appears at first sight, not because it's changing too quickly, but because our vision continues maturing. And that's beautiful in a way that requires no hurry at all. We can breathe, close our eyes, and imagine the beach. Out there in space's slow tide, shells continue being revealed where before there was only sand. And night after night, someone lights a more sensitive flashlight, points it at a small square of darkness, and discovers that there too was a galaxy, maybe dozens, maybe hundreds, waiting for silence to be long enough for us to see them.